And it's a bit annoying, right?
That's what I'm going for. So I'll do many times this. We just go to Dreamy Space. And he goes, yeah, so don't take in the week off again. So he gets it. Problem solved. But they also come back. And it's just, oh, exactly. So let's learn how to do that. Work out all the things.
But it may be, I mean, same as.
So which thing else away from that?
Oh, even a year ago, yeah. They might be. I know, because I see one.
That's 6 months.
Yeah.
Well, you just think it out. Why could we not read the bloody facts at the end? The fastest thing to do is take people's plans, or we get them out right. Sure. The intermediate, some of them go around for the 17th
In the middle of 2023.
It's just the logic.
Yeah.
We don't want to encourage that.
Yeah, so as soon as I was like.
It wasn't a possible timeline.
It's pretty cool though, like.
Okay. Anyway. What has it fossil? What has it another fossil? What was wrong with, say, conflict or any of the whiskies? Ranting about race control. We'll have to go and rant about later. That'll be fine.
Yeah.
It's okay, we've all outsourced our ranting to John. And we just want to sit there. Have you met Ross? Yeah, Nick Ross. He works in the same office, John. Somewhere in Google.
I would need
Big
your,
shit.
I would want to.
Okay.
It's been around about. That's no, you're for it. That's not much pain to find at all. If you decide.
Just the seven fish one, because
Yeah.
No, it's for us. It's like Game of Thrones, right? Like your house director A or your house director B.
Have you got to take out Bill?
You're either house director A or house director B.
We have nice simple divisions. We're either at the silicon bit, in which case we tell all of the people, the customers, no, we're not doing that. Or you're in the other bit where you come to us and our response to them normally is, no, we're not doing that because you can't prove it's worth doing. And then we just pick holes in their data until they go away. That's great. They all started hiring computer architects into the various customers so that they can come to us with more. We've got a whole lot of performance guys who are really good. Who come with wonderfully detailed presentations. And here's it again. And go and help those. You took them off. There's more important. Okay. Everyone needs to find great prefix control, which is definitely really close to user space.
What if your scheduler is better than everyone else?
No, it's a big question. What if no one knew
Hey, you must be here?
Yeah,
What if your
Nice to
scheduler
meet you.
is even better than our?
glad to have you here.
What was that?
Glad to have you here.
Yeah, likewise. Good to get to meet face to face.
Right.
Yeah.
So you're here for the confidential computing conference, or
Yeah. So this is my whole afternoon in this room, I guess.
cool?
Yeah.
Yeah.
Looking forward to the SVSM talk.
Mhm. Yeah, we kept it short. It's only 10 minutes because we have a block tomorrow.
Oh, okay.
Because we thought discussions might be lame, might be
Okay.
need more time. So
When is the Birds of a Feather?
it's tomorrow at 12:15
Okay.
p.m. So,
Okay. I might miss that.
in this room.
No, I should have. I didn't think about that. Yeah. Gotta order some.
Excuse me.
Yeah. Leonardo from Lenaro.
Nice to meet you.
Nice to meet you. Yeah, it's great.
Yeah, great to see you here.
Oh, the speaker.
Occasionally we use them. Like always, use them anyway.
I failed. Yeah, one thing I could have done.
Yeah, well.
Yeah, it's a board meeting tomorrow. I guess you're gonna have to leave the conference.
Yeah. There's officially, I think, voting to. Yeah.
The worst thing
It
is. Basically, you memory maps.
It's actually kind of small.
Well,
Maybe nothing compares to.
So we actually do it.
Yeah. Yeah, that's a decent sized budget.
Yeah.
Like the main thing.
You're gonna be the board, yeah, the board.
Should be good. Got time for Mike for himself.
So we find out
He's
it's
probably
probably
like
like
that. And then we can hire somebody.
No, I look at the
Both
boss.
sides that things for projects. A dev run person.
Well, basically, I suggest I have to.
Their name is Sal. That person is the only applicant we have right now. It's sort of a hard mouth. I think they were active and had open SSF arena and. Slurm? It's from, Futurama. It's nice. Futurama. It's like, they might make some how fast it's for you.
No one's, yeah, we've got no one's. How can we do? Who's better? Because always more. What you need? Yeah.
We can do Said you're working. Is there just the one up? Is there just the one?
He's asking if there's just one, like.
Oh, yeah, I've seen I've not seen another one.
Is it just one for them?
It's just one.
I'm instructing the.
Yeah. I don't need to. I think that.
4 minutes to go. T-minus 4 minutes. Checklist completed.
We're still missing that.
Yeah. He has not uploaded slides and he doesn't have sent slides. I haven't found an email with the slides. So.
Which ones?
I have not found emails. So when is this talk?
It's number 8.
Okay, so. I just wanted to upload my slides, but yeah, I can do it afterwards.
I don't know.
Okay.
Well, there's an intro, and then there's actually someone.
Yeah, towards unified confidential computing APIs, yeah.
And how much time have you given to the introduction?
5 minutes.
You know how to use PDB, right? So there'll be this thing on the top, you choose that. David, do you know if I join listen only or with microphone? This one. Here, do you know I join in with the microphone or just listen only?
Sorry?
This laptop.
On the laptop, no, you use the microphone.
So listen only.
Yeah, listen only.
Sorry.
This one's.
Yeah, I think you joined without the audio at all in that one. I don't think it's going through this laptop. The audio is all done for the OG desk.
Test. Is there anybody who has joined in remotely? Anybody wants to test their audio?
Yes, you're audible.
Okay, that's great. And it looks like we are at 2:30 p.m. here. Good afternoon, everybody. Welcome to the Confidential Computing Microconference. I hope you had a great lunch and are enjoying the conference. Before we start, just a few instructions to help make this microconference a success. Okay. So one, the microconference is only successful if we have good notes. So I would appreciate volunteers stepping up to take notes. There is a Etherpad session that you can write in directly, collaboratively, or you can send your notes in to me later. Then for the benefit of the folks who are joining in remotely, there is a throwable mic. Please use the mic, throw it around. I've been hit by the mic in the past, doesn't hurt much. But please use the mic so that our remote audience can join in. Discussions, good. We want to have as many discussions as possible as opposed to a Q&A session. Use the chat if there's a different talk going on. And discussions do not end here. Right? You can go have BOFs. You can continue on the hallway track. And with those instructions, let's get this microconference going. I'm going to invite Jörg up to start with SBSM.
Thanks, Tabar. Hi, and welcome everyone to this micro conference. I will do the first session about the Coconut Secure VM service module, which is only scheduled for 10 minutes because we have a lengthy BOF tomorrow. So any discussions that we get finished today, we can finish tomorrow in the BOF. So let's get started. So the Coconut SVSM, what is the state of the project? It was announced earlier this year, and currently it can boot a Linux guest at VMPL2 with on AMD SCV SMP hardware. It has core protocol support. It's getting CPL3 support. What we have so far is ELF loader, file system, basic support for tasks, basic support for virtual memory management. We support lots of checkers. We support Rust format. We support Clippy. We actually enforce both of those. So same as unit tests, we enforce those. We can run with Miri for Rust safety checks, and we even recently gained fuzzing support for certain parts of the code, which is currently around 12,000 lines. A couple more than 12,000 lines of Rust code is currently the SVSM. But this is about the future. So what is the roadmap? The current most important thing for the SVSM, which we want to achieve, and what has the highest priority is getting CPL3 support running and run a VTPM in CPL3. That involves some iteration over the syscore design and some more parts in the SVSM kernel part, but we are getting there. And after that, there are some cleanup work to be done. For example, getting rid of the direct map. Coconut still uses a direct map, which is not compatible with its claim that it puts a focus on isolation. Though there is some rework needed to get rid of that. More on that later. We also need a persistence layer in the SVSM, which is also one of the very next things after we have VTPM, because the VTPM needs to store its state somewhere and reload it after a reboot. So we need persistence. And another important part is support booting via the IGVM format. We can discuss that during the BOF. It's basically who has heard of IGVM or who has not heard of IGVM? IGVM is a file format defined by Microsoft, which basically allows to describe the initial state of a confidential virtual machine. So it describes the initial memory state, it describes the initial register state, so that a hypervisor can use the file to set up a confidential VM, and the customer can use the file to calculate the expected launch measurement.
Yeah, what does IGVM stand for?
I have to look it up, I forgot, sorry. Integrated gas, I don't know. I have to look it up. Right, the benefit of IGVM is that it also has information in it where to put certain hypervisor information like ACPI tables, the MADT table, or the memory map. And that is very, very compelling because that gives the SVSM a unified hypervisor interface, because it needs some information from the hypervisor, which it currently gets from QEMU via firmware config, and which we have to re-implement for other hypervisors. And with IGVM, we have all of that for all hypervisors that implement IGVM. So that's also one of the next things to implement. Actually, work on that has already started, but so what are the open problems that we need to solve, or that we want to discuss here, or that I want to see discussed? We can discuss other problems too. I already mentioned persistence. The design for that is not yet set. Do we want to use a dedicated block device? Do we want to use something else, like an object store or something? I don't know. We need encryption and integrity protection, of course, because every external storage is untrusted. But for encryption, we need to get a key into the SVSM, which is only known to the guest and the guest owner. So next problem. And we also need an access permission model to make sure that the TPM can only access the TPM state and other parts can only access their state. So this is our problem that need to be solved for the persistency layer. And besides that, there's also a deployment question. How do we deploy the persistent state for the SVSM? One idea I had, which we can discuss, is to store it as a separate file on the EFI partition of the disk image that we deploy. But there might be other better options. We can discuss that. Memory management, I already mentioned that I want to get rid of the direct map. This requires some more changes to the underlying code base, especially to the allocator and to the page management that is currently implemented. Speaking of the allocator, there are some other implications because the design of the Coconut SVSM involves partitioning of the virtual address space, not just between user and kernel, but there is a user part, there is a per task kernel space, there is a per CPU space even. So we don't use GS for per CPU data. We do that via the page tables, and we have a global shared part of the page table, or of the virtual address space. And in theory, we can allocate from each of these parts. So we need to solve the question where we want to actually do allocations from. Another big issue, I think, are our usage of Rust smart pointers. So currently we use the built-in Rust smart pointers, I think RC, ARC, and Box. Problem is that they panic on allocation failure, which is certainly not something we want, because it makes the project unreliable once we run out of memory. So we need smart pointers which can fail by returning an error and which can use different backend allocators. Because we might need to allocate from different parts of the address space, like a pure CPU allocation or per task allocation or a global shared allocation, for example. Apparently, all of this is already implemented in Rust smart pointers, but for that we need Rust unstable, and we just switched away from unstable Rust for reasons to stable Rust. So we don't have it from Rust. And it's not clear when these APIs from Rust will become stable. So yeah, I think we need to implement our own smart pointers for the time being and switch over to the Rust ones once they become stable. Governance, interesting topic, which we raised a couple of times already, also in the SVSM Devil calls. It's an ongoing discussion. So far, I'm the only maintainer, which is not a perfect situation. So the goal is to get more top-level maintainers involved and increase the buzz factor of the Coconut SVSM. But we need to discuss how to get there. And another list of possible next steps or other use cases for the SVSM, what can we implement or what can be done with the SVSM. We can talk about live migration. We can talk about a UEFI variable store in the SVSM. About epic emulation and secure IRQ injection. Support for more TE architectures besides AMD SCP SMP. And more device emulations and implementing a full paravisor even to run non-Linux operating systems or non-enlightened operating systems. Use the SVSM not as an SVSM for an OS, but also for as a platform for secure service VMs that don't run an OS on top, but that provide secure services to other VMs. Or any other cool idea that we can discuss or that you can bring up during the discussion. Since we have not much time today, there is an SVSM BOF tomorrow at 12:15 in exactly this room. So if you're interested, you are invited to join that. And with that, I'm at the end of my presentation, and we'll open the audience or the time for discussion. We have, I think, 4 minutes left. The rest is in the BOF tomorrow.
I just wanted to touch this thing. I do have one question. This might be like way beyond the scope of 5 minutes or not, but you mentioned smart pointers. And one thing I've been a little bit curious about with the SVSM lately is how shared memory and the Rust ownership model can play nicely together. Like Rust thinks that it has, exclusive access or whatever to a page, but in fact, that page is shared with the host. How do we reconcile these things? And do you think this is a place where having our own smart pointer might be able to help understand if a page is shared, or if it is shared, what is happening to that page?
I'm not the most experienced Rust developer, but I think it's difficult to enforce these ownership things with host shared memory because Rust has no way of tracking host ownership, right? Where we can, yeah. Maybe there is a way to tell that this page is shared with the host, so there is an owner for it. But yeah, I failed to come up with a good suggestion here. So it's where we get into the depths of unsafe Rust, I guess. So
Spend 30 seconds on predictable launch measurements.
predictable launch measurements. I hope we get that with the IGVM. So.
You said 30 seconds.
So yeah, that's actually the promise of IGVM, that you take the file, it contains all your initial state. You take it, you calculate your expected launch measurement, and you can compare it to the launch measurement you actually get and see if the hypervisor loaded your IGVM file correctly. Cross hypervisor, that's the idea, yeah. Once you're able to build a IGVM file that actually works cross hypervisor, but that's another problem.
Can you talk about some of the problems that you saw with direct map memory?
Yeah, so how Coconut was initially written is that it has some dedicated memory in guest mode and like 256 megabyte currently, and there's basically a direct mapping of that and a direct offset mapping in the SVSM to basically allocate memory from that SVSM owned part of the memory space. Now the SVSM wants to isolate between CPUs, between tasks, and we currently do that because we have per CPU mappings, but everything that's mapped in the per CPU space is still mapped in the direct map, so accessible by everyone. And we want to have it unmapped for everyone, or we don't even have it mapped for everyone. We want to allocate a page and map it then to whichever part of the address space it is allocated to, so global shared or per CPU, and that this page is then not mapped to anything else. So that's what we want to do to fulfill, or what I propose to do to fulfill the isolation promise that the SVSM gives, that the memory is actually isolated within the SVSM itself. Yeah. And I think with that, yeah, maybe time for one last short question.
A short question.
No short question. Okay, then if you have anything, you're invited to the BOF tomorrow. So thanks and have fun.
Next speaker.
Yeah.
Okay, so I need some help here.
Yeah, you go to the plus. Browser? The plus. Plus. And then you're number 3.
Okay, thank you. Okay, that should be okay. These are the old slides, but that's okay.
These are the ones they got from you.
No, there is a V2. But that's fine. So my name is Claudio Carvalho. I work for IBM. And I would like to talk about remote attestation of confidential virtual machines using a virtual TPM we have worked on. I'll give you a really brief introduction, and then we can discuss more about have a discussion. So let me first try to understand how can I go to the next one here. Okay, why do we need a virtual TPM in confidential virtual machines? The Trusted Platform Module, or the TPM, it's an industry standard, and it's used as it's used as root of trust for some of the services, such as measured boot and remote attestation. And the the virtual TPMs plays the same role for virtual machines, but the virtual TPMs that we use in virtual machines cannot be used safely in confidential virtual machines because the hypervisor would have access to the VTPM state, and the hypervisor is not trusted based on the threat model of a confidential virtual machine. So what we do is we run the virtual TPM inside of the confidential virtual machine. And with that, the confidential virtual machine memory is encrypted while it's in use, and then the hypervisor is not able to have access to the VTPM state. But to be more specifically, we run it inside of the SVSM. The SVSM is, as you already know, it's a firmware, and it runs before OVMF. It runs with the highest VM privilege level, which is VMPL 0. And with that, other softwares that runs with other VM privilege levels will not have access to the VTPM state. It would be protected. But in order to have this VTPM, we have to make a few changes to the TPM driver. And because now the TPM communication needs to go to the VTPM running in the SVSM. With that, also, we are able to reuse the existing TPM tools, the user space TPM tools, and also we are able to use OVMF code related to the TPM that populates the TPM PCRs. If you're interested more on the VTPM, you can have a look at that PR that I submitted to the Coconut SVSM. I should say that it's basically, currently it's running in the SVSM CPL 0. We don't have CPL 3 support yet, but when we have CPL 3 support, it would be easy to move it to running CPL 3 in the SVSM because the interface would be the same. Another interesting thing to talk about is this VTPM state. I said that the VTPM state is secure, but actually it depends on what we do with this VTPM state. The VTPM state is basically seeds, the key hierarchies, and any other object that we store in the TPM-NV, for example. An interesting question is how much of this VTPM state we need to persist across boots. And it really depends on the application. It depends on what we need, the application needs to do with the state. But for example, if we need to persist a VTPM state, generally speaking, we need to go through some steps. First, we need to generate the state, and then we need to encrypt. Generate the state, I mean the manufacture process, generate the seeds, and then we need to encrypt that initial state and securely persist it to a location outside of the confidential virtual machine, because if the confidential virtual machine crashes, we will not have access to this state. And then on every boot, we need to get that encrypted state, decrypt it, inject into the confidential virtual machine, and also load it, but load only if the confidential virtual machine is in the expected initial state. In other words, we need to do an early pre-attestation. And then if we make any changes to that state, we need just to persist it back to its original state, to its original location. So what I'm trying to say is, wherever this state goes, we need to secure it, and it would be difficult to secure in every steps. We started to explore other ideas, such as what if you have a VTPM state that is ephemeral? And by ephemeral, I mean, by ephemeral, I mean that the VTPM state is manufactured on every boot. And the VTPM state also doesn't leave the confidential virtual machine. And with that, it would be much easier to make it secure, I would say, because it doesn't leave the confidential virtual machine. And the first thing that we try to explore is the remote attestation, and we are able to do remote attestation using ephemeral VTPM. We have a proof of concept for that using Keylime. In the other slides deck, I had the link of you can see the V2 in the LPC. Yeah. Huh?
I said we'll upload the right set of slides.
You can see the link there, and it's. But I think I should not go to all the details. First, how much time we have? 8 minutes. Maybe we should start discussing, and then if you have time, we can go through the demo. I can try to get the link here. But basically, just to give you an idea, what Keylime does is just there is a setup, a Keylime setup, initial setup, and then the registrar. There is the Keylime attestation tool, and it runs on every boot and registers the confidential virtual machine. And then it goes to the next step, which is really the verifier that takes the policy and enforces the policy to say if the confidential virtual machine is or not trusted. But basically, it has to go through the launch measurement, validating the initial states of the confidential virtual machine. And then it goes to, it needs to validate the virtual TPM, authentic or not. And then it goes through the measured boot, validating all the way to the guest OS. And it can also do some runtime attestation, but for the demo that we recorded, it doesn't do the runtime attestation. If you want to know more about the attestation report, you can go to that PR. And we discuss other services that we can do with ephemeral VTPMs in this article that we published. For example, how can we do full disk encryption using an ephemeral VTPM? Okay, so I think at this point we are open for discussions, let's say.
Yeah, you have a chat question. You can read it if you want, but you can read it too. They want to know whether you're socializing your VTPM designs or collaborating with other platform providers or cloud service providers or other stakeholders, because there are many design parameters and it seems to benefit from wider alignment. And I have to ask, that question is way general. What does it mean? Because the VTPM is a standard thing from Microsoft. Everybody starts with the same thing. The TCG has one more TPM design reference implementation that is just attempted to implement in Rust, but it has no code. So there's really only one place you can start. And so what is the question about collaboration mean, since this is specifically designed to work with the AMD SVSM and no other platform has an SVSM currently. So if the guy who asked this question could actually ask it over audio, we might actually get more out of it.
Oh, he's typing.
I have no idea. Well, in the meantime, we should ask anybody else.
Yeah.
What's the difference between the SMP attestation report and the SVSM generated?
What do you mean?
The content.
The content.
You add anything to the report? Or?
Yeah, the SVSM spec, when we request a VNPL 0, an attestation report from VNPL 0, it also we also get some information from the VTPM. Some VTPM information, and that's a hash of the endorsement, the public part of the endorsement key. And with that, we can use that to know if the VTPM is the right one that you should be talking to or not.
So basically, it's the secure processor generated attestation report plus the VTPM
data? Yeah. there is a field in the, when we request a report, there is a field that we can put in the report, and then we use that field. We calculate a hash of the AK pub and put it there. Because it gets on.
Let's wait more to it than that. So the SVSM has a load of possible protocols that combine. BTPM is a design protocol, but it has a way of testing through the PSP at the field 0 that this SVSM has support for these protocols. TPM's protocol report is designed to contain the public key, public EK of TPM, which binds the TPM absolutely to the SVSM.
Yeah, that's the same running in that. Yeah.
James, David.
Sorry, no eyes in the back of the head.
So there are some open source frameworks, including one from VMware, that are certifier frameworks for verifying the attestation report that S&P generates. Are you thinking about using that in some way as a combined thing? Because at the end of the day, the owner is going to want to know that both the MPL 0 attestation report is genuine and the BTPM stuff is genuine. So is there some way to combine this?
Charles may have one.
So we have a little bit of the problem with which is the same that Claudio was talking about. You have to ascertain that the attestation report is correct. You have to attest that the VTPM signed it is correct. Then you have to compare the knowledge measurement with policy, which is why I was asking the question. So everything together, we didn't use the VMware protocol, but the protocols were described in the end documentation. So writing it down in Python didn't take us a lot of time.
I think for the VMware certifier, I don't think that there's you basically fundamentally have two stages of attestation here, one hardware thing. The verifier from VMware, I think, is really only going to help with the first stage at the moment, at least. And I don't know their plans beyond that, but I don't think it would solve problems here.
Wow. Yeah. Nice catch.
So quick question, wasn't very clear from this thing, but maybe each VTPM instance is uniquely paired with a confidential VM instance. There's a 1:1.
Yes.
Yeah.
Yes.
There is only one SVSM running that VM. So when we get the attestation report, it ties that instance of the SVSM.
So it's always a VMPL. It cannot be a separate confidential VM. And then because it's also VMPL, it's shared in that the memory management is using the same key as that confidential VM.
Yeah. Yeah.
Last one.
So just to make sure I understand this correctly, the hypervisor is still responsible for, you depend on the hypervisor to transport communications from the SSVM.
Yeah, the SSM, yeah.
But that's all encrypted with the memory encryption key.
Yeah.
So but the hypervisor does know the timing of this. So if the hypervisor knows this measurement will occur at this time, can the hypervisor just drop that write on the floor? Or is there any verification that the guest knows that that write actually went through to the SVSM?
We encrypt the communication using AES GCM, so we would be able to detect that.
Right, but if I drop it, the communication flow would then be valid from then on.
Yeah, we don't have much resource as we have in the kernel with timers. So for now, we are just invalidating the key, and you won't be able to communicate to the PSP to get a report anymore.
Okay, but if you then ask the BTPM for a remote attestation, that would fail. You not be able to
It will
ask for the
fail,
attestation.
yeah.
So okay, so it fails, closed.
So you close deal. No more communication.
Thanks.
Okay. Thank you so much.
Still talking.
Good job we didn't wait.
Samuel? Yeah. Hey everyone, I'm Samuel. I work for Rebos, and I'm going to talk about season 2 of my previous talk last year. I was talking about shrinking the elephant, and the elephant in the room was actual attestation. There was a lot of talk last year about the client side of the computational computing, how you generate, how you encrypt things, and everything on the kernel side, but not much talk about the attestation side of things. Can I? Okay. So yeah, we were talking a lot about the client side. How do we support attestation, computational computing in the kernel, in the guest side of things? But we're kind of looking at the remote attestation as a black magic thing that happens in the background and everything is fine. So why did I talk about this? Because basically what we're saying is that computational computing without attestation is not confidential. And that's one thing which makes attestation a remote or local attestation.
I disagree with that assertion.
You can disagree, yes.
Okay. There are use cases for confidential computing in the cloud where all you really care about is protection against others trying to attack you, and you're willing to accept the assurance of the cloud service provider. In that scenario, confidential computing attestation, provided the CSP assures you your setup confidential, still provides a huge amount of value to the tenants.
And how do the guests can verify this?
They don't need to. They're trusted by the service provider. So
yeah,
if you're on a track.
So it's confidential computing where it's confidential computing where you trust the CSPs. Yeah. Okay. So yeah, that's a different threat model. Okay, fine. I'm happy to yield you some of my time today, Mr. Chairman, because I think I wasn't sure there was a question, but your previous question was more relevant. So yeah, we're saying that attestation is important, and the problem we're seeing with this is that the remote part of attestation, well, the attestation part of things is very, very fragmented, or used to be very fragmented. The interfaces, the protocols, the formats that people use, and the manufacturer interaction, everything was very fragmented, very difficult to plug in. So basically, as a client, you get an attestation report from your platform, from your BTPM, SVSM, and plumbing that into a random attestation service is very challenging, or was very challenging. That was the pitch of last year's talk. And very briefly, to understand what we mean by attestation, I'm just going to go through quickly on the different step of attestation and why we think it's very fragmented, and what we try to or are trying to fix with the attestation service project. And really, attestation, the goal of remote attestation is that simple thing here, where as a guest, you're trying to get a secret from the broker, and the only way to get that secret is to be attested and have the broker deliver the secret to you, provided that it can verify that you're attested. How do we do this? From the confidential guest, we get an attestation report or evidence from the platform itself, and we provide that to a trusted issuer, something that's going to issue a key or a token that allows you to eventually get a key. This issuer then forwards this attestation evidence to a verifier, and this gets complicated here because the verifier needs to be able to verify all sort of attestation report formats: a SNP attestation format, a TDX attestation format, an SVSM attestation format, all kind of things. Every manufacturer, every project has its own attestation format. So that's already difficult. And those two blocks here combined together is what people call an attestation service, something that you provide an attestation evidence to, and it verifies your evidence. Once the verifier has been able to verify or look at the evidence, it will provide an attestation result. Attestation result as in, does it fail? It may be okay, it may not be okay, but it's a result coming from the verifier to the issuer, and then the issuer basically forward that to the guest as an attestation token, something that allows you to eventually get the secret from a remote party. One question that comes here is for the verifier. How does the verifier actually check the attestation evidence that it gets? And that's another layer of complexity that comes in, where you need to provide the verifier with a set of reference values, also known as golden values, that you're going to compare your attestation results, attestation evidence against. And also typically a set of policies where you say, yeah, I can compare this value against a set of reference, but I want this firmware version to be either 1.3, 1.2, or 1.4. What is it exactly? So basically those two needs to be provisioned in the verifier in some magic format, in some magic ways, for the verifier to be able to say, that's my attestation result. Give that to the issuer, and then the issuer transform that into a signed token that it gets back to the TVM. Then the TVM can use that token to actually get the secret. So it sends that token back to a secret broker, and the secret broker can even be the same entity as the issuer here. So you can have the key broker or the secret broker be the same entity, but it can be something different. So there's two different models, but basically you get an attestation token, you send that back to the broker, and you get a secret back if your attestation token is validated and shows that the attestation results are correct. So this is basically like a high-level view of remote attestation, and this brings a lot of complexity and a lot of proprietary custom things that are all over the place, and makes it very difficult to go from a client-generated attestation report to actually being able to get a secret. All the way here, you have different formats, different protocols, a different origin, where reference value coming from. So one very important one is the attestation evidence format. As I said, each and every manufacturer will give you its own attestation format. Some of them are somehow standardized or following some sort of spec that are defined by something else that the manufacturer itself. Some other manufacturers like Intel or AMD, they have their own custom binary format for the attestation report. So it's very difficult to build generic parser from a verifier point of view for this format. How do you get the token back to the guest? It's also completely open, and depending on the attestation service that you're talking to, you're going to get different formats. So you need to be able from the guest to manage and handle all those different formats. How do you send the evidence? Just sending the attestation report, the attestation evidence to your attestation service. This is already completely custom and open. Each and every service out there has its own thing. Oops. So that was the situation last year. We worked for the past year on a project called the attestation service. I'm sorry for not finding a more original name, but as part of the confidential and continuous project, we built this attestation service thing, which is precisely this. So basically, those two blocks, the blue blocks there on the right. So the attestation service project contains those two things. It's a completely open source. It's architecture agnostic. We haven't fixed the attestation evidence format problem because we're not silicon manufacturers. We cannot fix that. But we have implemented a verifier. So this part right on the right-hand side of things that gets the attestation evidence and is supposed to be able to understand everything, every manufacturer format. So we've built the verifier and we build it so that it supports all major attestation evidence formats. So you can send it a TDX, an SCV, a CCA, an ARM CCA, an SGX, an Azure VTPM format, CSV, which is a Chinese x86 manufacturer that do confidential computing, for those who don't know about this. There are some of those manufacturers. All those formats are supported by this single verifier. So you can generate and get an attestation report from any of those platforms, send it to this single verifier, and actually get attestation result back. We also support external verifiers. For those of you who don't know, Intel Amber, which is a Intel black box, let me put it this way, where you send not a attestation evidence, a TDX attestation evidence, and it gives you attestation result back, and you have to trust it. think. Anyway, but we do. So the verified block, that's part of the attestation confidential containers attestation service is pluggable. So you can remove that box on the right hand side of things and have the issuer, which is called the KBS, talk to an external one. In that case, Intel's proposal, the Amber thing. All the formats and protocol that we're using are open, as in specified most of the time by the IETF. So for example, actually, I have a more descriptive view of things. So for example, all the formats for the attestation results and the attestation token are using a GWT, a JSON web token. So this is something that's standardized by the IETF. So if you can read an RFC and implement this, or you may want to use existing libraries, you're going to be able to parse the attestation results that we get from this confidential containers attestation service. The protocol that we define between the guest and the attestation service is HTTP based, no fancy thing. It's very simple. It's a you give it an evidence, do some exchanges, and it gives you an attestation result back, all through HTTP, and very completely architecture agnostic. Same for providing the token to the KBS. So in our case, the secret broker and the issuer, the one that actually issues the attestation token, is the same entity. It's called the KBS in this project. We're also using HTTPS for provisioning our attestation service with reference values and policies. It's actually the same protocol, defined in the same protocol as the rest of the attestation service. But as you can see, there are a few things that we haven't fixed, obviously. One of the major one is the attestation evidence format. As I said, this is defined by silicon manufacturers mostly, and we can not really influence this. We can influence the one that are being defined, like the RIS5 one, for example. But the existing one is something that we can't influence, so we have to support multiple of them. The other things that we haven't fixed or kind of standardized is all the part at the bottom for the policies and the reference values. Which format do you use for those? And most importantly, where do they come from? So basically, your reference values are typically a hash of your firmware, a hash of your kernel, a hash of your user space libraries, and this should be coming from some sort of trusted supply chain for your software. So some trusted CI that gets into your reference value provider here and gives those values and provision that there. And it's a pretty big gap, and I mean, we're building all this security stuff, but eventually we're comparing our attestation evidence against reference values that we don't really know where they're coming from. And are they trusted? Are they not trusted? It's difficult to actually verify. And the origin is one thing, and the format as well. So which format do you use for describing a hash of a firmware and make it distinct from a hash of a kernel, and also make it distinct from a platform status? So do you want to know if your platform is running in debug mode, in prediction mode, and all this? How do you describe this? So looking at those gaps, how do we fix this or try to improve this? First of all, for the attestation evidence format, it's not really fixing it, but at least it's kind of making nicer. The configFS TSM ABI that Dan Williams has been pushing. It's basically a kernel user space ABI that allows for requesting an attestation evidence from your platform in a completely architecture agnostic way. So you have one entry point. It's a configFS based. You read it back and you get an attestation report. So instead of having a /dev/tdx and /dev/icv and /dev/ris5 /dev whatever, we now have one entry point for this. It doesn't really fix the fact that all those attestation format are just widely defined, but at least we have one entry point to get them. We just get a binary blob that we need to kind of know which platform is coming from. So as I said, the evidence format is still architecture specific. There are two architecture that actually took a nicer way, ARM CCA and RISC-V as well, that are using something that is not completely custom as far as attestation evidence format are concerned. And they're using entity attestation tokens, EAT, which is also defined by the IETF, sorry. And it allows you for parsing a set of claims. Basically, your attestation report is a set of claims for your platform, which firmware you're using, which status your platform is in, and you can parse that in a standard way instead of having to go through the hundreds of pages of the TDX spec to understand how your format is built. So yeah, if you're working on a new architecture, a new confidential computing architecture, please use that and don't come with your custom thing. The reference values, we're going to, I'm going to try to push for using CORIM, which is again, IETF defined format for describing to a verifier what your platform should be looking like. So basically, you give it a set of reference values, a set of states, and in a nicely formatted way and an easily parsable way. As I said, the big gap here is the link between the supply chain and the reference value provider. You're going to give it some values, but how do you verify that this is coming from a trusted build chain? The last thing that we're going to look at, is device attestation. It's another thing that I wanted to talk about. When you add when you directly assign a device into a TVM, then you must attest this device before accepting it. And by you, I mean the actual guest. The guest must verify and attest this device before saying, yes, I want it to be part of my TCB. What we're proposing is for the kernel to offload the device attestation part. So basically all the remote attestation thing, that the plumbing that I just talked about, to an entity called the Trusted Device Manager. The other part of the device attestation is that once you accept a device into your TCB, this device attestation result must be part of your overall platform attestation evidence. So now that your device is part of the TCB, when you send an attestation evidence to a relying party to a test of your platform, it must include your newly attested device, newly added device. So this is what we call combined attestation. Yeah, go ahead.
I misunderstood what you're saying, but are you suggesting that you cannot have the TCB changed, or you cannot test just the delta?
No, the thing is, the platform attestation not always happen at boot. It can happen at any point in time. Okay, so it can also happen after you actually accepted a device into your TCB. If that happens, then the next time you do an attestation, and you can do multiple attestation as well, after or before a device comes into your TCB. The next time you do a platform attestation, you have to include, because you're basically attesting to your TCB, and your TCB now includes this device. You need to include the device attestation results, because you already attested this device, into your overall attestation report. This is what we call combined attestation, where basically the attestation report not only includes the CPU generated attestation report, but also additional data, including all the devices that you added into your TCB. Then you send that to your relying party and let it verify that it's okay or not. So this is basically what we're saying. And yeah, we want to propose. Yeah, running out of time, I guess. Let me just quickly go through that. This kind of high-level view, where basically the guest kernel will detect a device and own the device, the device that's been assigned to a TVM, and the guest would rely on a user space component to actually run the whole attestation flow. The guest will be able to authenticate the device, detect the device, but basically the guest kernel probably doesn't want to go through an HTTPS endpoint and send attestation format, get attestation result, do all the verification by itself. So it would rely on a user space component that does the attestation. The same way you have a user space component that do platform attestation. And that component would basically run the whole attestation, send attestation result back for that device to the kernel, and let the kernel decide if it wants to accept it or not. And if the kernel decides to accept it, it tells that decision, it gives that decision to the TSM, who then opens the whole flow for DMA and MMIO. A very quick description, because I think I'm running out of time, but I don't know if I have time for questions.
One question, yeah. So more of a comment, like I don't have a problem with user space having a way to override or get in the flow, but I also think kernel components also want to get in the flow of attestation. So
yeah,
it may be the case that the kernel knows how to do some of it. It also has a user space helper that user space. Do you have an opinion too? Like I think you're going to get opinions from kernel side and user space side.
I think the kernel can definitely authenticate the device. So it gets a whole certificate chain from the device and can verify and authenticate the device. But the whole remote attestation process that includes talking to a remote HTTP endpoint, that's probably not something you want to do. And basically we can say the kernel is free to ask for an attestation result from this user space component and let it run through, get attestation results. And it's basically the only thing that this trusted device manager would do is pushing attestation results to the kernel and let it decide what it wants to do with it.
The problem with this is something that works in
So you could do exactly the same with the.
You have a special driver that connects to the TSM. The problem is we can't offer trusted device manager in its architecture on fundamental.
I think you can.
Okay, well, this is something we have.
I think you can, and basically the link between the kernel and the TSM would be a direct link between the kernel and the TDI itself through SPDM. Because in the case of the host use case, SPDM is established between the device and the kernel directly. In which case, the trusted device manager gives attestation results, and the host kernel would basically accept, which means in TD's parlance that it would actually move the TDI into a run state, which basically opened the whole IO flow. Yeah, we have another, it's not a buff, but it's a session, secure IO session. But yeah.
I think we're out of time, but that's the last question.
After it's came back, and you use that to talk to your secret. You register that JWK with your reference values, as in, if I have a successful attestation, the client back this JWK, and then how does that talk to the secret broker?
So the secret broker gets the GWT, which could be a key or something else, but it's a token containing the entire attestation result and signed by a relying party. So the secure broker can actually should actually take that, parse it, and understand if the attestation results are okay, and being able to verify the authenticity of this token. Then it can decide if this links to a secret that can be provisioned into the guest. But there needs to be a link between that attestation token and the guest. Yes.
So would there need to be a link? And the secret broker.
Yeah, which is typically why the secret broker actually runs in the attestation service. So yeah.
Okay. My friend.
Thank you.
Cool. I had a slight feeling that Samuel might take a little bit more time. So this talk is in some ways a placeholder for a general discussion about attestation, although please no devices. But anything else we want to talk about with attestation is kind of fair game. I want to focus a little bit more on the attestation client side of things. This is the piece inside the guest that's going to get the hardware evidence and then give it to a relying party to set up some sort of secure channel. That might seem like the easiest part of this whole thing, and it might be. It could be. But I think there's a couple of interesting and sort of subtle things to know about here. This talk does really build from some stuff that Samuel just discussed. I'm also another confidential containers person, and I'm not going to talk about that project at all here, but it's worth noting that we've spent like 2 years at this point building like attestation clients. And I know that there's some other people who are now starting to look at that a little bit more. Like in the beginning, we talked in Claudio and Jorg's presentation about like persistency in the SVSM. That's probably going to involve doing some kind of attestation, connecting to something, secure storage, something like that. So that's one use case. That's another type of attestation client. But yeah, you see, I actually added a question mark to my title of the presentation to honor the discussion format, and I hope the cube really flies. Ceremonial, can't go to the next slide issue. There we go. Just all future people, you got to press the right arrow key, okay? Anyway, I have like 3 themes here. And the first one, I kind of have something to really say. I know there's a lot of question marks up there, but there is one thing I want to get across a little bit, which is a certain type of security consideration that's worth thinking about that didn't really occur to me at all when we started on this attestation client stuff, right? So there's a question there to sort of get things started, which is about what's the worst possible thing that could happen to your confidential guest. And I think the first thing that comes to mind is that you could steal the secrets from the confidential guest, right? If you break into the guest, and a break-in might not be you dig a tunnel through the memory encryption. It could be that there's some sort of vulnerable software running inside the guest. That's more likely. In fact, what could happen? Well, yeah, you could steal the secrets, but I think there's something actually quite a bit worse, which is if you gain access to the ability to generate generic evidence that has a valid measurement, you can use that to impersonate other guests, right? And the question here is which other guests can you impersonate with this, right? If I can break into, let's say, the SVSM, just for the heck of it. Now with the SVSM, we are inside of VMPL0, so there's an extra hardware boundary there. So this isn't going to be easy, but let's say that we can do it. What would an attacker do? Well, they have the ability to generate attestation reports that look good, but they also have the ability to put any host data they want into it. So where we can't go stealing attestation reports in flight, just off the network, because they have a nonce and they have the hash of a public key, something like that in them that binds them to a connection and a guest. If you're inside of the guest, you can make really anything that you want. So you could use that report to connect just about anywhere. And the question I think that's really crucial and worth thinking about is who can you actually attack, right? And the answer to that kind of depends on what the evidence looks like, right? And in particular, if the evidence is extremely generic, then you may be able to attack anybody who's expecting something that looks a bit like that, right? So for the SVSM, for instance, and this could change, you know, if everybody out there is running the same SVSM binary, and it turns out that there's a way to get into it, if one person is able to spin up a VM and break into that SVSM, then they have evidence that they can give to any verifier that's expecting an SVSM to run really anywhere, if it's the same binary, right? And that's pretty dangerous. That's this term I sort of refer to as like this evidence factory, this ability to use even your own VM on your own machine to open up an evidence factory that can then go attack people very widely. I think that's worth having in the back of your minds. It might seem obvious, I don't know. So first of all, does that like make sense and seem like a valid thing to people? Okay. The real okay, that's good. We got to reflect that for the people who are watching online. Oh, good point. And by the way, James, did you finish your discussion with the previous guy or? Okay. Anyway, I think the interesting question is what can we do about this, right? And I have 2 things to propose, 2 strategies. They're kind of interesting. Like I said, this is particularly pernicious when you have a like generic measurement. So one thing you can do is not have something as generic. Of course, that is a bit of a pain sometimes, right? Because we don't want to complicate the process of verifying measurements. So we don't really want to have every guest look different. Now, with platforms like SCV, SNP, you have different components of the measurement. So you might do something like use the host data, which is set by the host, to put something unique in there. And then when you show up in the guest, you're not going to be able to use that report to do a bunch of different things with. I'm hand waving a little bit. To actually get those properties, you need to be pretty careful about what you put in the host data and how you use it. But generally speaking, what I mean is that there are ways to make a report not generic without changing like the guest memory layout every single time. Although if you're using SEV, then you may have to do something like that, actually change the layout of the guest. And I think it's worth noting that there's a profound tension between something that's generic and really easy to measure and something that is going to give you maybe better security properties. We kind of want generic things to simplify our lives, but you need to be a little bit careful. The other thing I want to propose is I think maybe even more interesting. And one strategy to deal with this is to somehow revoke access to the ability to generate a report at all. So this would allow you to, for instance, be inside of a guest and get one attestation report, but then say, this guest will never generate any more. And that means if it turns out that your guest is somehow breached, somebody breaks into it later, they won't be able to generate a whole bunch of reports and use them for other things. There are ways to do this, like with SEV SNP, you can delete the VMPCKs. Those are the keys that you need to talk to the PSP. Now, doing that will have some other consequences. And I think I already know that some people in this room don't like that idea, so feel free to complain about it. But that would make this kind of attack pretty difficult to do. For TDX, it's actually a lot simpler to do something like this because you could just modify really any PCR with any random value, and you would essentially poison the measurements so that you can't use, the same sort of report.
You actually have this differentiator if you want. Upon the guest card talk, so the owner can provision, a couple of details. Unique. You have this first part, which is not generic, and that's being attested as part of the report as well, attestation evidence.
You're referring to something like the MR config, which can be set by the host, or?
All this owner, an ID and things like that.
Yeah.
So that's exactly like how you separate.
Both the platforms have the option to be able to do this, but not everybody uses these. In fact, I think most people do not use like the host data, for instance, because it's more complicated and adds more steps. And again, what you do with that, there is some subtlety. Like if you just stick a random value into that field, then your verifier is going to need some way to figure out, like, wait a minute, is this a valid report? And there might be ways to like track and make sure you don't get the same one twice. The other values I might put in here are like the URI of the verifier, like the URI of the KBS or something like that. So I think there are strategies surrounding that. But currently, I don't see very many people who are implementing this stuff using those things.
A lot of those are in.
Yeah, I mean, the key thing is that those things are set on the host. And so when you show up in the guest, where we're talking about this exploit of being able to generate these new reports, it's already set in stone at that point. But yeah, it is complicated because the host controls this in the first place. Yeah. I mean, I guess what I would say, just, I feel like I can't quite get to the real subtlety of this here without a little more time. But the one thing I would say is that if you're not careful, the way that you configure the host data can make it so you can still do an evidence factory attack, but you can only do it one VM at a time, right? So if you craft the right host data to fit where you're trying to attack, you could spin up one VM that would be able to generate this malicious report. You wouldn't be able to use that VM to generate a ton, so it's a little bit better, but it doesn't get you a lot. But I do agree that in general, like these approaches of being less generic stem from that, yeah.
Yeah, I'm not I follow the host data argument because we have to assume the host is conspiring with the guest, and the host may be the one who launched the attack on the guest CSM. The ID block, I think, was what.
I don't know if it's battery changes. I'll repeat your question though.
The ID block is a signed thing that the guest owner can provide, which makes the report unique for that guest. Yeah, there's not ways to customize it.
Yeah. David was saying he's suspicious of the host data because it's set by the host, but the ID block, which is signed, is another alternative. And I think that's true. I think the ID block is potentially a good solution here. I'm even less aware of people actually using this feature, but it seems like a good way to potentially.
Is there a barrier to using it? I mean, like, are we inventing something because nobody's using the other thing?
Is there a barrier to using the ID block?
Yeah.
I think not fundamentally, maybe complexity and maybe at some point, support in, various tooling.
David, you said you're wary of the host conspiring with the attacker, but if the host data is somehow rooted into CSP PKI, that seems less like the evidence factory seems to be from some highly malicious attacker who is not a CSP. But I guess you're worried about the evidence factory being a CSP, which that seems pretty unlikely given contractual agreements. Yeah, agreed.
Yeah, so one way like that we've talked about resolving this in confidential containers, to give a very specific example, is that you put in the host data like the URI of the KBS that you're going to connect to. Then this is checked by code inside the guest that is measured. So inside the guest, this must be the KBS that I'm going to get all my resources from. And even if it's set wrong by the host, doesn't really matter because you'd just be connecting to some other KBS. This is a kind of a subtle question, though, when we start talking about identity in particular, which I think is still one of the subtlest parts of confidential computing. But I do have 2 more themes to maybe get to. So, although, like I said, I'm happy to just, right arrow. I'm happy to really talk about whatever people want to talk about. Another thing that I think is an interesting thing to be aware of is what metadata we pass to the verifier. And Samuel actually alluded to this a little bit in his talk. Obviously, all of the protocols he laid out, we're all in on that, right? So this is all good stuff. And my presentation is sort of building on this about how you should design various components. One thing to keep in mind is that you probably don't want to just throw the evidence at the verifier and say good luck. There is some metadata already associated with various platforms. But if you look, for instance, at the launch digest that you're going to get from a number of various different platforms, it's doing a lot of heavy lifting. It's generally a hash, and you typically don't really know what's in it. If we're talking about like the RTMRs for TDX, that's a little bit nicer because they usually have a log that goes with them. And if you think about it like a TPM log, that's the metadata we're talking about here. That's how that's how that problem is solved in sort of traditional attestation land. But when we're talking about like, what's in my launch digest, it's pretty hard for a verifier to know that on their own. I want to draw one interesting distinction here about sort of like internal ways of doing this and external ways. I'm not sure these are the best terms exactly, but one way to resolve this is to have some sort of tacit agreement between the host and the verifier, right? And another way to do it is to have something inside of the guest that tells the verifier, right? So in one of them, there's some sort of agreement between like the owner of the guest and the CSP, like, hey, I'm using the CSP, so I'm sort of expecting these things, so I'm going to tell my verifier to expect these things or whatever. That doesn't really require anything inside the guest, but it requires you to have some sort of agreement here, which is really not formalized. And then there's another option where you do this in the guest itself, and the guest actually goes to the verifier and says something about who it is or how it booted or something like that. Can we give Samuel that?
So what I'm going to say is not solving the guest identification stuff, but I talked about the EAT format for this, and it precisely it's a descriptive format for an attestation report, as opposed to one gigantic hash that covers everything that you measure. If you take AET, you can really describe what's in your attestation report, and you don't need to give a hint if the platform gives you that already.
And just to build on that, if you like the IETF RATS model of attestation, you break verification into a verifier and a relying party, and then you have a policy, a relying party policy that you can put some of these domain-specific reference values into that the person who actually cares about releasing a key or something like that can validate. And then a quick plug for, there's an attestation working group in the CCC, and if you Google that, we've got a repo that has all of this alphabet soup of different sorts of EATs and CARs and so forth from IETF and TCG and everybody else.
Ears, don't forget the ears.
Back on what Samuel said on EAT, would that be generic enough to take into account that each attestation report is different? Like you've discussed before, each architecture has a different attestation report. Would EAT be generic enough that it can still work for all of them?
And I guess the biggest problem with this reference values and format which we're talking is that if we can generalize the platform specific part, because like if you can kind of hide that behind saying what, like I don't have to go start to understand, okay, I need to provide TDX module as vein, something else which is specific, something else for IMD and so on. So that part would be the most beneficial.
It is specific, and you can customize it with vendor specific extensions that, I mean, anything is better than just a 256-bit value. You get a 256-bit value with some tag associated to it. So we can actually understand what it means instead of saying, yeah, this is that. What do you do with this? You need to know that, oh yeah, TDX at offset 78 is placing the hash for this. With EAT, you can actually parse it with the tag and value proposition.
So how much time we got? Last question. Let me just show the last slide in lieu of the last question. There's also a question about networking. The attestation client needs to be able to reach the KBS somehow in some places this is really easy, in some places not so much, like the SVSM may not have a network stack inside of it. So you could have a proxy on the host where you use some sort of simple serial device to connect to it, but that requires some level of coordination from the host that we might not be able to assume exists on a wide variety of, CSPs. So this is a little bit of a puzzle that still may need to be resolved. Okay. Key broker service, relying party. Sorry about that. Yeah, although we also talk about JWT.
JSON Web Token.
Yeah, JSON Web Token. It's a form.
It's a crypto token that you can pass through HTTP, basically.
Okay, I think Tom is next. So thanks, everybody.
Thank you. Do you have a break?
At 4.
At 4?
Yeah, right after this talk.
All right. Hi, everybody. My name is Tom Ladaki. Did this presentation with Pankaj. He can't be here today. I'm going to talk about SNP live migration, but the general scope of this is to talk about what we can do to make a common API that all of the Cocoa VMs, or as much of a common API as we can, that all the Cocoa VMs can use to do a live migration if they need to. So one of the things that we're going to have to do for live migration with SNP is we have to use a VMPL0 piece of code. We're probably going to just use the SVSM and add live migration to it. Jorg had mentioned something about that a little earlier too. And what we'll end up needing to do is when we start the destination QEMU, we're going to need to communicate down to the SVSM and have it generate some attestation information. It'll generate a public-private key that we're going to use on the source side in order to generate a transport key. We'll generate that attestation report using the hash of the public key in the report data, and then make that available for when the migration begins. The source will then request that migration data, validate it. We'll go through making sure that the report data contains the hash that we create from the public key we're given. And once we validate all that, we can then create a transport key that will then wrap with that public key and send it back to the destination. And now we have a way of being able to communicate the private data between the source and the destination QEMU. So the steady state migration, shared pages, just done in the traditional manner. So source just sends them, destination just receives them. But the private pages, we need to do something a little special. So we need to call down through KVM into the SVSM, gather some metadata that can include things like whether or not the page has been validated already, the GPA associated with that page, and any other security information we need. We will encrypt the guest page, send the contents back up with the metadata, send that over to the destination, which will then process the metadata, take the page, decrypt it, and place it into the guest memory. So this continues on for a while until we get to the migration completion phase or the blackout phase. At that time, we'll prepare any pages that haven't been migrated yet. We'll take any state for vCPUs, VMSAs, package those up. If we're running things like a VTPM in the SVSM, we'll package that data up, transfer that all over. And on the destination side, it basically just unpackages everything, gets everything ready, and as long as everything's good, we'll shut down the source, start the destination, and we're complete. So this is where I want to really aim the discussion is what do we need to to create so that we have something common that we can use across TDX, across S&P, across CCA, anything else, if it's possible.
Just for clarification, the SVSM runs at VMPL1, so in this case, you're actually kind of stealing CPU time from the CPUs to do the migration work?
So the SVSM runs at VMPL0.
Yeah, 0, sorry.
Yeah,
The other way around.
we'll probably have some like shadow vCPUs that are gonna like spin up. I didn't want to get into the details of what we'll actually do for SNP as opposed to talk more about the APIs. But we'll probably spin up some shadow vCPUs that will handle the requests from user space to package up the pages, right? And that would have to also track what pages are moved, and there's multiple ways we could do that with marking pages read-only through the VMPL so that any writes get triggered back as NPFs, or we could, depending on how many pages are left, we could, almost try and do like a hash of what we think the content should be versus what was sent and things like that.
Yeah, the reason I'm asking is that a while ago, I think it was for SCVS, we were thinking of having a shadow VM that handled the migration, because at the time, of course, you could have things mapped into separate VMs, which is not possible with SMP. And we decided, it was never implemented, but we decided to have 2 VMs because there was issues like you would be able to call from one vCPU and inject the APIs into the migration helper. That would have been a mess. But I guess this is does not apply here because you are at VMPL0. So you still have a trusted, like the migration is part of the trusted base here, right?
Right. So what we're going to need is, and I'm looking at it mainly from, say, a QMU point of view, but anybody that has their own VMM would need something, right? And I think TDX already has kind of a GitHub repository where they have some patches already and have done some work towards this, but we need APIs to initialize some of this migration, right, and communicate back and forth between the source and desk about this, so that we can generate the migration data we need and then transfer it over to the source so that the source can validate the destination and get that working. Then within KVM, we need to be able to allow QMU or the VMM to call down to then talk to the SVSM. Right, so trying to split it up, but I think QMU and KVM is my focus, and KVM is probably more what we want to talk about here. For the steady state migration, we need to be able to take the GPA that's being asked to be moved, package that up, and get it over. I think TDX is doing something different where they have epics and they're doing VSOC. And I think they do it all in one kind of steady state call. I'm not positive. I need to examine those patches a little closer, but I'm wondering if that is necessary, because I'm not sure if everyone can make use of that same model, or if we want to make everybody use that same model. Migration completion is kind of just that same thing.
Are there
for the
use
final
cases
state.
for live migration beyond wanting to upgrade the host? Because if the only use case is upgrading the host, do we have any confidence that this is ever going to be less complex and more performant than getting the host reboot really fast? Because if we can pour all of our effort into making the host reboot really fast instead of doing the insanity, in my opinion, that is live migrating S&P and TDX guests.
But it could also be if you have issues with the platform that you're on, that maybe you're starting to see uncorrectable errors or correctable errors.
The main problem is platform failure, and you have that in Google Cloud as well. Your machine is failing. You need to coordinate. You need to get everybody off. That's a live migration we have to do, and we can't reboot it.
why can't you reboot it though? Like, I understand that your customer's like, I really don't want you to reboot. Bad memory, like I get all those, but are the MTBFs for those things on these platforms so bad that we have to migrate? Or can we eat those as a, look, your performance is going to be so abysmal while we're migrating you. Like, do we have that confidence or we just don't know yet?
Do we know that
Just the platform is bad. It's the fact that we're on an older platform and the customer demanded we have a newer platform. We have to shift everything across. And they want their virtual machine to stay running when we do this. There is a lot of use case in the cloud for migration to different systems. There may be use cases for upgrade migration as well, but we have to do both.
Yeah, I just want to say there are still other use cases like for heat management of the fleet, defragmenting, packing better. Yeah, I think there are that this is definitely a primitive that we want, live migration of SCV S&P. Yeah.
I just had a comment on I think live migration is probably still important for those scenarios that James also mentioned, but on the perf side, in my past life, we had done some analysis where really the deltas you're talking about is once you've identified the lifecycle points where you're migrating pages, is the encryption, integrity generation, information and integrity verification, which with the right hardware assist can bring the performance down. So we had done some analysis where things converge at a reasonable point. You're not adding gobs of overhead. If you apply the right hardware on those points, really, it's really those points, right? The overhead is the generating of the export time integrity information, the MAC that goes with the pages, and the verification on the destination. You mentioned the encryption and the integrity. Did your protocol also keep the replay protection on the memory as well?
Depending on the protocol type.
Yeah. Maybe you should have someone go up there.
No, it's fine. Depending on the protocol type you choose, you can slipstream replay protection into it. An example being is GCM. But then you have to correctly select your method of data transfer. That's why we had, that model, we had the epoch kind of model, because you have to generate initialize the IVs on both sides correctly for AES GCM to work correctly. So yeah, there's a lot of details in the protocol, but it's achievable. If you select the type of protocol, then you can get replay protection as part of the data transfer.
Is the protocol public?
I believe it was documented in the white paper from Intel. Again, I'm not speaking for Intel because I work at Reverse but yeah, I just know enough about it.
I think you're done. Does anybody see any problem on how we do the steady state as far as calling down, whether it's, migrate this page range and getting a bunch of data back versus just.
I guess it says receive final state, and the state diagram wasn't super clear on the past slide, but do you also plan on supporting target brownout, basically where target's paging in from source, or is it only can the target run while paging in old data from the source?
You mean like a post copy?
Yeah, post copy demand paging.
Not initially. That's probably something that we can look at as like the second phase of it to see how we can handle that.
Just one more thing on the APIs. So there is another way of doing live migration where it's done through DMA, and the source droplet reads the memory out through DMA, and without the VMM process actually really getting involved. I just want to say I hope the APIs, I'm not quite sure, but I hope whatever the APIs you put together will work for that case. That it's probably, I don't know. If
it would have to probably be DMA'd after the page is packaged, right? So that, because the source and dest are going to have different ACIDs, different encryption keys.
Right. So you'd have to say package this page, and then, but provided the API at least puts it somewhere which is DMA accessible, then the DMA can pick it up and carry it over. Yeah.
So CXL 3.1 is out today, and one of the features in there is to allow you, I had to get it in there somewhere, There's a bunch of stuff in there that would allow you potentially not to move the memory at all and do the migration. So, because you'd have it on a remote device, and you'd migrate there, and then you keep using it all the way through. Extra fun.
I just thought we were trying to get less
Can you go back to your last slide, please? So your design involves migrating SVSM state, right? Or the whole SVSM itself?
No, we wouldn't migrate the whole SVSM because the SVSM is going to be running already on the destination. So you could almost use it as a way of upgrading the SVSM too, if you think about it. But it would be more for things like VTPM state, right? So that you can continue with TPM operations. Anything within there that kind of is used by the guest. But overall, you know, the SVSM would be started new on the destination side.
Yeah, okay, that's good, because what I had in mind was that we don't trust the host hypervisor to help us in migration. What we only want from the host hypervisor is the dirty log and the secure and the channel to the destination VM, and the rest should be handled inside the SVSM, I think. I'm not sure how that flies with TDX and other architectures, but that's to be determined.
There is a missing state on the migration completion. We need the final step to be destroy the other VM, because we can't have migration used to clone VM state and then be used to attack the different states that we clone.
I don't know if we need a KVM API for that versus just making sure that the SVSM would have to know to kill off all the guest vCPUs, basically mark them non-runnable so that they can't be run anymore. Right. So as long as you trust the SVSM, we're okay there.
Yeah, I guess SVSM can do that as long as it's the endpoint for that protocol. But again, in the replay protection thing, as part of that transaction commit, yeah, you do want to also use that replay counter as part of that last token, a special metadata token that you send to the other point to say the transaction is actually completed, so that you make sure the TSM on the source endpoint makes sure that that VM is not runnable anymore because the transaction completed.
Last question. There's one at the back.
I guess two comments. I feel like we're going to need all the same kind of architecture for TDIS live migration, because that's also going to happen. And I'd also like to ask, when you do your live migration, can the attestation change?
The attestation, and Jeremy or David will be able to talk a little bit more about this. I think initially we're only going to support going from same machine to same machine, because the attestation reports will be drastically different between, say, you know, 3rd generation Epic, 4th generation Epic, and then we're going to have to add policy, right? And so once we get into policy decisions about, okay, what is a valid attestation report from say a newer machine model to an older, and make that decision.
You've put the policy inside the SVSM, and then you've got the policy in the previous talk in the relaying party, and they're not the same policy necessarily. So isn't this like opening up a security hole?
So it depends on how we're going to do the attestation of destination, right? And if we start with, you know, same generation family machines, we can just compare like reported TCB fields and things like that within there, right? But if we have to start adding, you know, like the next phase will be to support migrating either to, you know, newer machines or older machines, whatever is needed, right? But we're going to need some policy there on what is allowed, right? And how we go about that.
Well,
we can talk.
Yeah.
If I'm
yeah,
not,
there's a lot of,
maybe I'm not
there's a lot of,
understanding exactly what you're.
No, it just sounds like we've talked about this in our world too. It just sounds awful. Like you're basically saying you change the attestation. So why did you attest things if the hypervisor environment can change them at will? What was the point of attesting them in the first place? Or you don't get to change things that you want to change. Like you can't upgrade your BIOS, you can't change your processor because all that becomes fixed and attested. Like it just doesn't make sense to me.
Maybe we can talk offline then, and I can
So
better
you can-
understand. Yeah.
It doesn't remove the products.
Right. Right.
You can redo the attestation and have it still pass and still validate, but if you want to avoid time of check, time of use issues, then you need to have an atomic way that as part of that switch, you need to not have the attestation for the old machine be valid in the new context that you don't know if you can trust anymore. And just real quick, one way to do that is have a secret that's non-exportable. And for a bunch of prior art, look at what hooks had to be added to the user space interface to do things like support forking safely with OpenSSL to drop secrets in there. Anyway, there's a whole bunch of inspiration to take from those things.
I was just going to say thank you for the discussion. We should keep this discussion going outside. We have a break going back now. We'll be back at 4:30.
Nope, we can get to the AV guys.
You still living on in California?
No, I moved to Halifax a while ago.
That's provided by the hypervisor. The other thing that the guest kind of do is to determine the host it's interesting, yeah, the question is, there's nothing we can do about it, right? Yeah, you're right. You can't trust the building, but we also don't have an it's all we have right now, right? You might ask if you have to implement something like a page modification or guest side. Yeah, we need on the guest side, right?
Come on. What is it?
No, yeah, exactly. But then you Yeah, it's basically just going, hey, we need this page to the SPSL. Whether it be, I'm afraid that actually page again. Yes. It's not like what was done like. Yeah, and it went through KVM to just like, okay, give us, just kind of. It wasn't different than the problem. Yeah, we can still use very lots of, but when it's not supported, this is not supported by get trapped up like the end of the we can do it two ways, right? Or through the VMPL position, we can mark all of VMPL. Just have to basically go everybody say anytime about issues like we're generating. Yeah. Everybody getting on. But then there's come right together. Going to spit out. Maybe what would it look like if you spit out one that's so because you keep the dirt. Yeah, There is, in order to, otherwise you're maybe we could do how, and now we have security. How we kind of do their it looks like they're not ready for the next meeting.
Where you're extracting things, how you're extracting things, that's just
but shining the light on it. Has been able to. Oh yeah, maybe we should. When can we understand
I always go the route of let's just.
The problem is given that it's, you know, the same family, like just my everybody went through that. I don't know if that's the attestation could be different based on that can happen That's kind of now that we finally were able to publish this stuff just to change the names and not be like, no, we're gonna have an open call. We're ready for like. I know. Probably the running Microsoft meeting is like the only one Microsoft is like having some clearinghouse. A difficult hardware vendor doesn't want to take the body. It's the way you go. Get on board. The Greek cycle was already passed, but exactly. Yeah. So you want don't figure out the software to tell ones that are wanting to do a product that is you can enroll your own server from there. Small stuff goes on. But their concept of what's oh, like their cost to external complexity. Because at the end, it's like, what the hell is this? Like, yeah, you got multiple levels of things. But it doesn't say, like in the end, it doesn't give you a data. So if you do split, you have to do it.
My understanding is that so averse to building, even though so much momentum that trying to do something different is not selling to
But like, I'm reading fast, and people mention DX, and I was waiting for somebody communication, show them the thread, and like, DX, this is my traditional curriculum. And then all of the internal discussions. We can show up with this, but we went to the thing of the
It's really hard having gotten this maybe in Intel and especially if you want someone telling you versus actually not having to use all of their software in order to realize disruptive thing. If you don't have that first-hand experience, some customer that's going to see even though it's
even validated my entire Who do you mean by us? But I mean, like, but in terms of like trying to get something like, sorry.
So I didn't see anything expected. Yeah, I don't have to create yeah, there's like two paragraphs. One
all the TP images are not going to behave the same as you would expect.
Yeah, because yeah, so some amount of customer education is happening as we say. I understand we have software.
It's fundamentally not a TPM.
By the way,
Check, check. Hey, hey. This is about the only extra one we have. I'll make do with this.
Closing the door.
Okay, that's the best I can do on short notice. It's also mine. We can stand and talk.
Thank you. Okay, hey everybody, welcome back. Hopefully it was a good break. Everybody's ready for the next part. So this next session is on secure IO, and I just want to preface this with a quick background here. When we came in, we had multiple proposals talking about secure IO. So we, in the spirit of LPC, we just combine them all, and we are trying to force all of those guys to come and talk with each other and bring it up. So I'm going to ask Stefan, Samuel, Jeremy, and Tom, and Dan. Let's try to get you guys up here so we have a mic to pass between you. And then the throw box can go around. And Stefan, I think you get us going.
Like I say, stay away from the screen.
Okay, so I want to shed some light on how the Astro90 guys do this. So as you might or might not be aware that we do things quite differently. I think I'll keep myself telling that over and over. But we encrypt the guest completely. So the guest kernel, the guest image RMFS, and the parameters are encrypted with a private key, or with a public key, and the private corresponding key is baked into the hardware. And the hardware is part of the trusted computing base. And so we trust our firmware as well. So we don't have to test firmware, but that's a different topic. And the part that's not trusted is only the hypervisor and KVM stuff. And again, we trust ourselves as the guest. So the main point is our image is encrypted. And for secure I/O, we also, as a completely virtualized platform, trust our devices that are plugged in, as these are only trusted devices that are plugged in. And if you have a non-trusted device or a non-valid device that's plugged in, the firmware will reject using it. So the device is already trusted. And so we have different I/O devices that we want to have an additional layer of security. Mostly or only cryptographic accelerators and EP11 cryptographic coprocessors. And the issue here is that especially these EP11 coprocessors have key material that's bound to a session, and the session has to be handled out. And for non-confidential I/O, the host can inject that key handling session. So we need to find a way around that. And therefore, we have two steps. First one would be binding the resource exclusively to the guest. It's done via firmware. So, and we trust the firmware, so this is a secure process. It's just a simple process of sending a CPU instruction.
So you don't need to accept that in the device explicitly.
So
firmware, you don't need to explicitly accept the device, the coprocessor, in the VM.
No. So if there is a device available, we know this device can be trusted.
The decision be up to VM to decide. So I think that we know that the device is trusted, but who are we? Because it shouldn't be up to VM to decide. This is the device. This is its measurement certificates. Do I trust this or not?
Yeah. There is a way for the guest to verify that this device was signed by IBM, which I did not cover because that's for I/O, and I have looked more the way from the conversion to computing side.
So the tenant of the VM has a way in advance to kind of communicate what type of device, out-of-bound communication, what type of device is trusted.
See that this is a signed up device. And the other part we do is the association step, and that's more or less create a secure channel to the EP11 adapter and create a session. And this session, for sake of simplicity, can be seen for now as a TLS session, more or less. But it's not, but it's the same idea. And all communication is done via this session material. And this all session and key material is bound to that session. And if a KVM want to intercept it, he would see only garbage. And more or less that's from the SV90 side. I just wanted to give like a presentation or an overview that we do things differently, and probably you have like different angles of what you want to do. So that's more or less stuff I want to talk about.
Okay, so I'm going to talk about the RISC-V secure I/O definitions, and I have a couple slides, but I've been asked to present TDISP first. We're going to talk about TDISP, and this is I have 5 minutes to do all this, so bear with me. The TDISP state machine is a trusted I/O specification, and the state machine that you see here is a view from the device itself. So within the device, each and every virtual function, for those who are familiar with the SRIOV, is going to follow this state machine. Unlocked is basically how the virtual function is at reset. Then you lock it once you actually want to pass it to a VM. The VM gets to see the device, and when it accepts the device, it asks your firmware, your PSP, your TSM, whatever you want to call it, to move the VF from locked to run. By that, it means to say, I'm accepting this device, and now I want to actually use it and run it. So you have those three states. If, for example, when in lock mode, you assign the device into the VM, and if the host VMM tries to mess up with the configuration of your device, it's going to switch back to error state. And you cannot, it won't do any confidential transfer DMA into your memory or anything like this. So in both locked and run states, if anything happens with your device, if the host tries to mess with it, or anyone but the confidential VM tries to mess with it, it switches to error state and all confidential data is wiped out.
By device, do you mean card or function? Let me repeat the question.
So by device, do I mean card or function? I think we have to distinguish the two. By device, I mean function. So it's called a TDI or virtual function, and it's different from the actual physical device, the PF, that can be split into multiple VFs, and you assign a VF into a virtual machine. When I talk, this state machine here is applicable to the virtual function, not the device, the physical device itself. Does that make sense?
Yeah.
Okay. IO, this is the RISC-V secure I/O specification, and I want to emphasize that this is, I'm driving this together with someone else from Intel, Jiwon, who could not attend this conference, but I think it's interesting that Intel is driving a RISC-V hardware specification.
Just in case.
Just saying. It's not a typo, that's what I mean. And to unlike IBM, we're trying to not do things differently. We're trying to be very, very boring. We're trying to do what other, when we think other architecture do a reasonable thing, we try to follow the same things. So we're trying to be very standard and boring, basically. So what I mean by this is that this is an overloaded diagram, but we only support PCI devices. We talk to the PCI device is the link between the function, not the device. The link between the device and the host is secured through IDE, which is another PCI specification. The TSM, the TSM talks to the physical device through something called SPDM. So it authenticates and connects to the device, establish an SPDM session, and then use SPDM as a transport for sending TDISP. I just talked about TDISP. For sending TDISP requests and getting the responses. So PCI, TDISP, SPDM, all standards, and I think this is pretty much what AMD, Intel, and AMD and Intel actually are doing as well. Yeah.
A little bit more about what
you want
what SPDM stands for and what ID stands for.
So ID, I don't know SPDM is, yeah, it's a letter soup. I don't know, but it's basically a way to establish a secure logical channel between two endpoints, and it's used in many different use cases. And in that case, it's for establishing secure, encrypted, replay protected channel between the TSM and the DSM, which is basically the firmware running in the physical device. You establish an SPDM session, and you have a logical encrypted replay protecting link between your TSM, your firmware, whatever is running your computational computing platform, and the device. And then IDE is the physical link protection, the PCI physical link protection. So you want to protect that as well for physical attacks. And the Cove IO is a set of two set of ABIs: the host ABIs, which runs between the TSM and the host VMM, and the guest ABI, which runs between the TSM and the confidential VM itself. So most of the specification is basically about defining those ABIs and the flows related to it. So ABIs and flows. ABIs and flows, the very high level flow is to go from connect. Connect is basically the host VMM assigning a virtual function into the confidential VM. And by doing so, it asks the TSM to establish this SPDM session that I just talked about between itself and the physical device. So now you have a protecting link that you can use to do the binding, which is basically about binding a specific virtual function within this physical device to a TVM. Once you've done that, it's all happens from the host. The host has bound a virtual function into a TVM, but the TVM is the one actually deciding if it's worth, if this virtual function is trustworthy or not. To do that, it's going to run attestation if it wants to, and eventually call into a guest ABI going from the confidential VM into the TSM to tell the TSM, yes, I'm accepting this device into my TCV, please start it. And by start, it means please move the virtual function from locked TDISP to run TDISP. When the virtual function moves to run TDISP, basically means it's going to be able to do DMA, and it's going to be accepting TLPs and doing MMIO into the device. So you can configure the device, and the device can read and write your confidential memory. So yeah, that's the flow. I'm running out of time, I guess.
So that was a good introduction here, and in fact, this is almost the same flows, but with different words. So this diagram shows essentially what an untrusted device looks like whenever we need a device to touch. We need a device to touch a guest memory. We can't allow the guest to be able to. We can't allow the device to be able to touch guest private memory, and so we have to bounce buffer that through shared pages. And so what it's chewing up is processor time to make that copy. So TIO and TDISP in general is trying to essentially eliminate that problem, that bounce buffering. So by allowing this binding operation between a device and a guest, we can eliminate the bounce buffer, because the device, once attested to and accepted by the guest, the device can touch private memory directly. So here are the different words. Essentially what happens here is that we have a device connection that happens, and that's when our SPDM session is set up. And then the guest can be launched before or after this happens. But there is a time in the life cycle of the device and the guest where the TDI is bound to that guest. And that's done through a firmware command we call bind. And then once the bind operation happens, the guest has an opportunity to check the attestation reports and the configuration of the device. And it will do that during this flow in the bottom here, where the guest does the attestation checking, and then it will validate, for instance, the MMIO ranges are appropriately mapped into the guest. And then it will also turn DMA on after attestation to say, hey, now I'm going to allow that device to touch my memory. One interesting, I suppose, distinction between the previous slides and this is that the AMD flow will and go straight from the unlocked state to the run state, because we will rely on the host's IOMMU and RMP checks to prevent MMIO and DMA maliciously attacking the guest, which is, we don't rely on the device to prevent that. So PCI traffic, it's built from this IDE, 2. We have the IDE stream that we talked about. It's keyed by our security processor, the TSM. For us, it's the ASP, the AMD security processor. And these keys are set up at device connection time, and there's basically a global IDE stream for an entire physical device. And so all traffic is going to flow between the host hardware and the physical device over this IDE stream. So we also want to enable secure MMIO. So we want to make sure that the MMIO ranges given to the guest are actually mapped to the right places, that we're actually touching the device that we intend to, touching the TDI that we intend to. And the security processor is going to provide this TDISP interface report that will describe the locations of these bars to the guest, and validation happens there to make sure that that checks out. And then we have secure DMA. So we have a way to tell the IOMMU through programming a device table entry, a secure device table entry, which is a new data structure that we're going to be introducing, that enables DMA and allows the guest to program the guest specific fields of the device table, which include its page table pointers and other things. And the guest will provide that data to the security processor, and the security processor will program that on behalf of the guest. And that once you program that, DMA is ready to go. I think that's it.
Awesome. Can I question?
Quick question, like seeing your slides again and getting a flashback about Tostadale.
Flashback.
Flashback, I think, from KVM farm, right?
Yeah.
Same slides, or similar at least, same concepts. The main thing I'm pondering about right now is what prevents me as malicious device from replaying an attestation that is non-good.
The device can't so if it's a bad device.
I'm a bad device that also implements TIO.
Mm-hmm.
I basically copy, I license the IP blocks to allow me to authenticate, yada yada, and then instead of giving you the attestation that would actually.
Your report is signed
By whom?
the device manufacturer.
Well, I'm the device manufacturer, and I just copy the. I copy the.
Manufacturer, you keys are leaking. Yeah, that's.
No, so I'm saying I'm building an FPGA. That FPGA is a man in the middle, maybe, I don't know, something.
So this is like the CA infrastructure. So the question you've just asked is, what if there's a bad CA in the infrastructure? And the answer is, well, everything falls apart.
Yeah.
So Acme Device Co. has their own root CA that's going to sign all of its device identity keys.
So the attestation also includes another crypto key that then becomes the actual data encryption key. So without,
it's a signing key. It's like an attestation key on the device.
It's just a signing key, the encryption key that actually plays. Okay, no, it's not like TLS. That's the main problem.
It's like SPDM is like TLS. It's secure key exchange, a secure authenticated key exchange protocol. So just now, instead of TLS certificates, you exchange this. SPDM provides you to exchange this, measurements, certificate chains, and so on.
Okay, so you use the attestation and something in the attestation, some public key, to then do the actual encryption afterwards.
So the SPDM allows
An ephemeral key, yeah.
Yeah, allows you to generate this ephemeral key.
That only if I actually have the private side of this, can use. Okay.
Certificates to authenticate and PHE to.
Yeah, it's identical to TLS, authentication ephemeral key.
Okay, back to you.
Yeah, the station is signed by different.
There you go. It's not as simple as that. SPDM covers both. Sorry, get this first. SPDM covers both, but you're correct that you're using the certificates to sign the attestation reports,
Once that's done, the other thing you're doing is setting up a bunch of ephemeral keys. If you get into TDISP, you're setting up 3 layers of ephemeral keys, all of which are posted over the previous layer as you authenticate your way up. Only when you get to that point can you do some of the key setup for the encryption of the link and all that sort of things. It's an amazingly nested stack of encryption.
The only way to accept a device into your TCP, a malicious device into your TCP, is if someone has managed to actually steal a private key from the device manufacturer and put it into your firmware. And if that's the case, everything falls apart.
Yep.
Not even that, so you can pin.
Not even just steal from the device manufacturer, but you can also pin the cert of, oh, this is the device that I expect in this piece of hardware. And unless I have some evidence that I intended for some tech to change this card and this machine and this rack, then it's you can pin it for the lifetime of the machine. So it's not even like well, it shouldn't be a break once, break everywhere. I mean, obviously, if you steal the root CA keys from the manufacturer, then but
I want to call time on this discussion so I can hijack the discussion for my questions. And also, I didn't have an Intel slide to precursor. I'm not AMD. I should start off by saying I'm not supposed to be here. Like I'm the CXL maintainer. I guess I got an mmap flag up once, and so people think I can go and wrangle other things upstream. But I'm basically here to help wrangle some of the stuff upstream. But I wanted to step back and ask or pose some framing questions about. So you saw the RISC-V thing, you saw the AMD thing. I'm not gonna touch the S3 or anything, but the RISC-V and the RISC-V and the AMD thing look similar to what Intel is building, and I didn't have the same level of detail slides as Jeremy, but that's kind of the point. I don't want everybody to have to if the entire community has to speak, are you talking about RISC? Are you talking about AMD? Are you talking about Intel? Like we won't progress as a community. Like I think the complexity will kill us. But the framing question I started off with was like, what if there was a standard across vendors? Like, wouldn't that be grand? The problem is we're not there. These things have high amounts of momentum that have already occurred. So next question is what do we do? But also given that there's some fundamental complexity that we all need to solve together, what's the best way to get us all in the same boat, rowing together? And so towards getting in the same boat and rowing together, I wanted to propose some principles, and feel free to question the principles. That's the whole point of being here. But the principles for me were, of all these, now that we have like several examples, we can evaluate and look at them and say, what of all the primitives these things offer, like what is the coarsest grain one? And where coarsest grain to me means like the least amount of complexity exported to Linux, because I care about solving customer problems without doing a lot of work myself. So like the more we can push into what the platform provides, that feels like a better starting point for the community. So I'm looking at the solutions and evaluating them on coarseness. And then in terms of making progress, like there's a lot of use cases that people want to do with these things. And I want to say like, we'll get to those, but we want to pick one, and it's going to be, and we should pick like one that's ruthlessly simple, and basically where almost everybody's crying, like this is not going to cover everything, but it's going to get us to the point where we can say, phase 2 is we increment from this foundation versus trying to get everything into the foundation. So people like to call it minimum viable product, but it's kind of the kernel enabling golden rule of like, do the simplest thing first and then add features. So that's what I mean by being ruthlessly simple. So I drew some pictures of what I think ruthlessly simple looks like. Also, I must say that this isn't simple, but it's declaring like where things belong. And so like if you and the good news is, like I took a look at what AMD was doing and like where they do IDE key management, and I looked at where kind of TDX had it in the first instance, and TDX kind of had it in a place where some of the key management was in the VMM and quite kind of coordinated with the TSM. So the proposal is, hey, that's too fine-grained. That doesn't satisfy our first coarse grain principle. Let's move that below the TSM boundary. So like that, when you understand that the IDE key management happens in the TSM for AMD, you also understand that IDE key management happens in the TSM for Intel, and we don't have to have upstream discussions about why is this detail leaking out. We can push it below this TSM boundary. So.
TSM key management, just to make sure I get this right.
Yeah.
TSM key management is basically policy, right? TSM key management means these are the devices I believe I should accept.
Well, let me define what a TSM is. So TSM to me is it's also the term that TDISP uses, but it's the TDISP specification uses, but it's basically the platform component that is able to that the VMM is going to trust to set up secure relationships with devices and provide you reports, and it's going to be the communication interface. And correct me if I'm wrong, on AMD, the TSM is the PSP. They have the security processor with a firmware interface that's been there forever, and it grew some TDISP-like capabilities. I don't know if it describes more like TDX or is it, again, more yeah, a software TSM or open source. Well, like open source project or open source. Okay. To me, there's a difference between open source project and open source. But anyway, so this TSM boundary we should have the same verbs going up to the VMM to bind. And so when we're talking about these verbs, are things like you both said the word connect. Like let's agree, connect is the established SPDM setup IDE verb. And then we both have the concept of bind. Bind happens from the host side. Everybody agree that bind is the verb. We're going to talk to the TSM. So it's basically going down the line and defining these verbs across vendors, and then asking vendors that come along and say, hey, can we leak this detail above the line? And we'll say, well, no, like this is, we can have discussions about is this above or below the TSM boundary. I do think there's going to be, of course, there's going to be glue layer. Like so, in this slide, I have like it probably isn't big enough for the whole room. So the green box is the TSM thing. It has an SPDM kind of initiator in it. One of the common things about these TSMs is even though the AMD thing is like a processor, I guess I don't know if it's not powerful enough, or I don't know, but it basically ended up with the same problem that TDX had, where we didn't want that thing to be doing the actual MMIO to do the config cycles. It actually comes out into a service in the VMM where the TSM says, hey, send an SPDM message with this payload. The VMM sends it and then hands it back to the TSM. So the first level of what we need to do to support TSMs is we need to have this SPDM dispatcher. We need to help some of these restricted execution environments affect things in the host. I also had another dispatcher over there that I want to call it out as a way to more quickly handle some of the TSM details on the TDX side, which is, hey, inside. So the TSM on Intel is actually the TDX module, which you may have heard about, and then there's something else called this TPA TD, which is like it's a helper guest that's going to do some TSM operations, basically admitting that the TDX module can't do everything. We need another trusted component in the system, but that we can hopefully. But the plan is to encapsulate this behind the TSM, so that you don't have to worry about those details. But that thing might need to make calls into the TDX module that we might, similar to how we have an SPDM dispatcher, we might need to have a command dispatcher. I don't know if RISC-V needs something like that as well. Give me the mic.
Or just.
I think one of the limitation and why you need a separate TD is because the TDX model is not interruptible.
Yeah, yes, it's a limit execution environment. Yeah,
so you don't want to have it generate keys or that kind of things, and that's why you have a separate TD.
Right.
RISC-V is different. Yeah, it's interruptible, so we don't need like a separate operation.
Yeah. So the whole point of the discussion was to run out of time, so that didn't have questions. But we're gonna have a BOF tomorrow to go into the details. But that was the framing I wanted to get across today.
I still want to ask about the policy part. So you have this TSM module there, right? That is going to eventually have to decide whether to accept the PCI device or not.
No, the TSM job is really just to be a trusted intermediary.
Who decides when to trust?
The guest.
The guest decides and he wants to trust the device. Guest is the host assigns the device into the guest. The host assigns the device into the guest sees the device, but it makes the final decision of accepting it or not. And it makes that decision and communicates it to the TSM.
And accepting is binary.
Is what?
Accepting is binary. Like either I don't accept this device,
Yeah.
and that means I cannot use it,
Yes.
or I accept the device, and then I basically give it all secrets I ever had.
It's not defined, so this is something that we're working on. We need to create those ABIs for the guest to actually tell, do I accept or reject or something else in between. This is open for discussion. This is why we're here.
Okay.
But it's the decision is done by the guest. The guest is the final decider on TDISP
leaves that implementation defined. Like as far as TDISP is concerned, like once it's in the run state, it's like
exactly. As
it's
far as
off to
TDISP
the
is
races.
concerned, it's binary. It's yes or no. That's right.
We're ending this discussion here, but we have a BOF tomorrow.
When? Tomorrow?
Yes. Now I know it was in one of the slides. What time's the BOF?
At 4:30, I think.
Okay. I will let you know.
Ming
Wei next.
Okay, I will start this section now. Today, Mingwei and I are going to share our journey on tamping the incoherent cache issues in confidential VNs. So this talk will be organized in two parts. First, I will give some background on the problem we are trying to solve and explain why we have the incoherent cache lines in the first place and how a patch fix introduced the performance degradation. And the second part, Mingwei will show how we use the MMU notifier to solve the problem as well as mitigate the performance impact. So let's get the ball rolling. The whole story starts with the design of the CBIT in SME, which is Secure Memory Encryption by AMD. So CBIT is a bit in the physical address to mark whether a memory page is encrypted or not. So when enabled, when CBIT is enabled, then all the memory access will be automatically decrypted and encrypted by the hardware. And assuming we have two addresses here, and the only difference is the CBIT. So the memory management component in the kernel actually recognizes the CBIT. So it knows that these two addresses are pointing to the same physical location. However, the CPU cache in the hardware doesn't recognize the CBIT. So from the CPU cache perspective, the CBIT is just part of the physical address and also part of the cache tag. So you can imagine that there will be cases where these two cache lines can physically lie in the same piece of hardware at the same time and pointing to the same pointing to the same physical location. So depending on two different dirty cache lines will eventually result in independent write-back operations. And depending on the timing of the write-back operations, you might get into some trouble. So that's the case study to see why that is a trouble. So let's assume that those addresses are page addresses. So at time T0, we have the confidential VN or the set VN owns this page and writes some data into the page. So at T0, the first cache line with the CBIT equals to 1 will actually show up in the hardware with some dirty data cache. And then this page might be released by this set VN and then to the host, and the host might reallocate this page to another non-confidential VN. So when the non-confidential VN writes the data into the page, at the T0, you will see the second cache line with the CB equals to 1 also show up in this piece of hardware in the cache with some dirty data, right? So you can see that at this moment, at T1, there are two different cache lines with different dirty data lying in the same piece of hardware. And later, when the first cache line, the write back operation was triggered first for the first cache line, this dirty data from the previous confidential VN will be written into the memory of the non-confidential VN that owns the page right now, and you got data corruption, right? So the solution, this is the basic form of the cache incoherent issues that we will be discussing today. And the solution back in 2017 was pretty simple. We just do the cache flash whenever the set VN gets the page or get destroyed.
Yeah, until we fix the hardware. Yeah, there's
Exactly.
mitigations.
So, do you want to ask questions or?
I mean, AMD is fixing hardware. They have partially fixed hardware on Milan. So the original issue was you weren't even cache coherent within the same CPU. They've got that resolved. They forgot about DMA, so that's the next level of thing. Allegedly, I think there's going to be a full featured fix, but so it's yeah. Yes, we've got them to consider.
I will cover this part very shortly. So in 2020, as Sean mentioned, like AMD actually roll out a CPU feature called SME coherent. And this actually recognizes the CPU cache to recognize, enable the CPU cache to recognize the CBit, so that they can enforce the cache coherency in the hardware level. And later in a patch, we just skip all the cache flashes whenever the CPU has this new feature. And in 2022, we actually report a vulnerability and managed to crash the host from the user space by triggering the same cache concurrent issues. And it turns out that, as Sean mentioned, like this SME coherent can only enforce the cache coherency between the CPU processes, but not when the DMA devices touch the page. So this is actually a day zero issue since Ceph was introduced. And we also figured that restoring the cache flash that we mentioned in 2017 would not work because the previous a VMM can actually bypass those cache flashes either maliciously or accidentally. So our solution is to do the cache flash using the MMU notifier when the page leaves the confidential VN. And when we post this patch to the upstream, we actually receive some reports on the performance degradation because we add some additional cache flashes to the system. And we also realized that some specially designed workload can also trigger those unnecessary cache flashes. So next, Mingwei will talk about how we still feel that MMU notifier is the best place to do the cache flashes and how we can use some information inside the MMU notifier to actually limit the performance degradation. Okay,
Thanks, Jackie. So yeah, let's get to the second part. But before we get into details, how can I flip? Arrow key? Okay. Yeah, before we get into the detail, I'd like to spend 1 or 2 minutes, maybe recap a little bit, so make sure we understand the problem. So it's cache incoherence, right? And the solution is simple. We flush. What's the problem, right? You know, we start the VM, we allocated data, we allocated memory, we flush cache. When the VM dies, we flush the cache, right? The problem should be solved. Unfortunately, well, if we think so, yeah, there's no problem, seems to be, right? That exactly follows the lifetime of VMs. But further investigation, we shows that actually our VMM is able to control the cache, the memory allocation and deallocations. Therefore, it is able to basically unping the memory and trying to do something funky, right? In this case, situation may goes off the track, and then we see that SME coherency is actually not effective. Those kind of worm cans are opened. So this is exactly the situation is, right? So because of the VMM, right, a non-root VMM is able to manipulate the state of the confidential VM, so you can deallocate memories. This will lead us into the very awkward situations. That's why we goes into this little bit brittle, but still the most effective, the most, working with minimum changes solutions. That's why before we get into details, I'd like to clarify a little bit. So in order to solve this cache flush problem, so what's the big deal, right? The first thing we want to improve is like, hey, can you flush the cache just for that VM? Is that possible, right? Isn't it idea? Isn't it supposed supposedly what we should do, right? Unfortunately, because of the existing MMU x86 implementation, this is non-trivial, right? And that is why it is not covered in this presentation. We would spend majority of the time doing for the first, actually the first case, where we only flush cache under circumstances where the KVM understand that is deallocating the guest memory to the host, because that is the only case where things will go wrong, right? So in order to do that, right, we go to the second page. Yes, we have to talk about MMU notifiers. Why do we talk about these details? Is because this is the only interface where KVM is hooking into the memory management systems. So KVM is a secondary memory, like IOMMU, right? Basically it says, I don't care about physical memory, right? I don't directly manage that. Whether the physical memory is located talking to the host MM systems, I only care about two things, mappings and TRBs, right? For mapping and TRBs, we can do some optimization to do. This is where we're standing in between. You can see this line, MMU notifying validation range start. We're supposed to be walking the KVM host page table, but that's kind of non-trivial, as we already mentioned, right? We can also go to the right-hand side, but doing host page table walk at MMU notifier is also difficult. So because of that, we choose to say, hey, we, as a simplified version, we can still say, hey, we flush the whole system cache, but we do it very carefully because there is a reason parameter inside MMU notifier event, basically coming from the host MM saying, hey, I want you to zap all of the memory pages mappings. By the way, here's the reason. Oh, I am doing M on map. I am doing M on device. I am migrating your pages, right? For those reasons behind, there are actually 8 of them, right? So we can select, okay, for these reasons, if you're really deallocating the guest memory, we flush the cache because that is the only choice we have, right? We want to do it simple. We want to make sure the security properties retained. For other cases such as, okay, I'm actually doing M protect, right? I'm changing the permission bit of those. Those are fine, who cares? It doesn't matter. The guest memory still retains in the VM, right? It's still in the VM process, right? For those reasons, we can give a kind of, clarifications and filtering out, and so that we can drastically reduce the number of cache flushes to reduce the performance regressions that we may generate to other VMs running the same host. And yeah, so that's the most effective approach. So that's what we can come to a conclusion. Yes, so I would like to leave the rest of the time for the questions, please. And any of them. Okay.
So trimming down the number of cache flushes from KVM seems like a no-brainer, especially if we don't have to make changes to core MM. Like, that's not controversial. Is there anything beyond that we actually want to do or need to do? Like, are we actually trying to solve anything? Because if people are doing NUMA balancing with SEV VMs, can we just tell them don't do that on this current hardware because it's not going to work, and turn that off and not try it? And like the unmapping thing, like you mentioned, a malicious user space. Like if you're unmapping on unmap, then you have a different problem. You need to rate limit your write back and validates. So like what beyond the flush less with the existing mechanisms, which is not controversial, beyond that, is there anything that you're proposing?
Yes, I think you're right. You raised a good point. So there are several system level behaviors, such as like MM trying to migrating pages, and those kind of things are actually incompatible with this approach. Basically, they're just shooting, right? MMU notifier first, and then the page is pinged.
Yeah, but
okay,
like,
I can do it.
sorry, at a higher level, are we talking about we want to improve performance and fix known issues, or are we talking about theoretical things that because we are going to get hopefully hardware that doesn't have this problem, it's not a problem for SMP and TDX because we can just deny access to the pages. So it's a very specific set of VMs that are at this point becoming not legacy, but more esoteric than they were even when they launched on hardware that is going to be obsolete at some point. Is this a problem that needs to be solved beyond the obvious things? Or can we just say, don't do that, it's going to hurt?
Yeah, I think for the question like this is like for SEV and SEVs, we have to do that, right? Like we have to do something like this. But for SMP, there might be a better way to do so.
Why though? like, what is the use case for having anything that's going to randomly migrate SEV pages?
Right, other than attacks?
But attacks, this does not prevent attacks.
This does. This could prevent attacks because
if your attack surface is I can migrate pages to trigger write back and validate, you have to rate limit your write back and validates.
right, you're saying that you're saying that this is actually a performance attack. Is that what you're
I'm
talking
asking what is the problem that we really want to solve? Because if the answer is, oh, it's this edge use case, then we just tell people don't do that edge use case because to solve this in the kernel is crazy complex and you're going to have hardware that fixes the problem.
You can, right? Like VMM is not controlled by the kernel, right? This VMM is actually in the thread model is untrusted, right? So that's basically the things like
what I'm asking. But
no, that's a fundamental because the VMM is able to do that at runtime. Our confidential pages can be unpinged, can be moved at any time during the lifetime of the VM. So that's why we have to do this on the MMU notifiers.
I know
stuff.
Ashish has a
Yeah.
question, so maybe we'll get him and then we'll get to you, Dan.
Yeah, I just wanted to say that we did some profiling with the MMU invalidation notifiers and different reasons. And the clear was kind of the clear event which you talk about as filtering. We did notice that it's used for multiple reasons, advice, zapping, and all that. So do you think that is an event that you can filter out, or it's when I did the profiling, I did notice that it's not an easy event to filter out because it's used for so many reasons, and it's not just and on top of it, it's one of the main events which causes most of the performance issues, specifically with, load balancing and KSM use cases.
Yes, thanks. Yeah, this issue is well acknowledged. So basically, the memory notifier reasons may be overloaded. There might be several things sharing the same reason, but this should be fixable, right? Like if we change that, adding new memory notifier reasons, like clarifying different memory notifier inside the host MM, we can solve that problem, right?
You're saying that you coarse grain you do a little more, you put the clear thing to be a little more coarse grained. Kind of thing.
In a coarse grain solution, turn off those troublemaker stuff, page migrations, NUMA balancing. Don't move those pages. Make sure those pages aren't moved. Then your system is safe.
You're already a couple of minutes out past.
Thanks.
And the real question is, should we just remove all of the legacy SEV stuff? That's actually the real question we should answer. All right, off we go.
You can hold on to it. Yeah, you might have questions about this. Yeah, so me again, not supposed to be here, but talking about something. So this, I happened upon a patch set for TDX attestation reports, and the claim in one of the discussions was, I think I saw an email from Dave like, why do we need another character device in Octal? And I think the justification coming back was like, well, AMD got away with it. Can't we get away with it too? And the claim was like, oh, like there's no kind of framework for this. And I was like, hold my beer. Let me put this together. The assertion is that if everybody is doing the same thing, they should probably be doing it the same way. And this is a hard concept to get across to the kind of the back end of that, the saying, oh no, but the TDX is different than SMP. Like the adaptation reports are different. But like a funny thing happened, even posing this question, is that like this started off as a keys subsystem thing, and James like this doesn't belong in keys, but James was able to had an opinion like about like this should be unified but not here. But then the keys people got involved and they started talking about like the community started to grapple with something. Like once you say, hey community, this is going to be the common thing, people come out of the woodworks to start to define it. Like, and once you kind of try to put it into vendor corners, like nobody reviews it, and like I think it shouldn't be the case that you're trying to get away without people not reviewing your stuff. Like and the goal of bringing these together is that people have a common language to negotiate things. So it's just better all for the community if we're all behind the same ABI. The other thing is that also I learned a lot about attestation reports that I knew nothing about before I started this, was that there's some nascent efforts to try to do an industry standard on this, but things haven't come together yet. But this kind of points to an operating system's role. Linux's role is kind of the consortium of last resort. It's especially like we're the last link in the chain that has to deal with the differentiation. And our first inclination, our instinct is always say no, like don't differentiate, like if you don't have to. So kernel has a role here to try to get the standardization that didn't happen beforehand. The other role of the kernel here is the keeper of the ABI. So if somebody rolls their attestation report format in a binary incompatible way, the bug report is going to go to the kernel, because the ABI contract that the kernel exported to them was violated. So that's a kernel bug report. So the kernel has a role to play in trying to enforce that those things don't happen. One of the ways that the kernel, this combined interface does that is by putting people's attestation report formats in the kernel's ABI documentation. So if you've read the documentation and you've written your thing to that format and that format changes, that's a kernel bug. That's you've broken ABI, and kernel has we have ways of dealing with people that break ABI, and one of those ways is like, hey, it seems like you're not ready to stabilize your format. Maybe we shouldn't be exporting them at all. And they go, wait, no, we won't break it. So like, there's those kind of those are kind of the only things that the kernel community has to get kind of ABI compliance is code acceptance, like and the threaded rebirths. We don't really have other mechanisms. Except I wanted to highlight this as an opportunity. Like I know Dan posted this proposal about having people come together. So in terms of trying to get to the point where we have a forum to do these things, I just wanted to highlight, I don't know if you know about this process called Code First. It works amazingly well in the ACPI working group. The ACPI specification moves kind of slowly for publication, but an open source moves fast. There's several cases where the Linux community or the Tiano core community, they identify a need for a change well before that consortium does. And the way that process works is you develop the idea in the open, and then you ask the consortium to ratify it, and they say, yes, this will appear in the next spec. But it bypasses this whole kind of confidentiality, can't talk about it for a year kind of problem. And the idea here is maybe this is a forum where we could have a code first process for confidential computing, where we say, hey, it'd be really nice if all the vendors agreed about this and ratified that in somebody. And I realized I didn't actually introduce what we're talking about here too well. Let me. The right arrow key's not working, guys. What? At the graph presenter? Oh, okay. So what this was is that SEV and TDX have a way to ask basically the TSM, the same thing we were talking about before in the last presentation, the TSM, give me an attestation report of the state of my VM. AMD has a format, TDX has a format. The going in position of this solution was that we're going to accept that those things are different and say, okay, here's what you have today. These are the formats, but we're going to transport them over a common transport. Actually, let me show you this data structure. I love this data structure because you could basically implement pretty much any ABI on the planet with outblob len, oxblob len, oxblobs, like blob blob blob. But I mean, but at least it gets us to the point where we can talk about the transport and people can have discussions about, hey, what do you guys put in oxblob? Oh, we put a certificate store in a specific AMD format. Oh yeah, oxblob over on Intel is the same thing, but in the Intel format. At least it's like put the same things in the same places. We do so, but back to how people actually use this thing. So there's a TDX guest driver. There's a SEV guest driver. They both call TSM register. They export this TSM interface in config.fs, so you can make as many of these config.fs instances as you need. it is config.fs, so you do need some user space brokering if you think people might collide on that. And then you just say, hey, here's 64 bytes, because both Intel and AMD both need 64 bytes. They get the report out, and it comes back out in the format. And it's pretty dead simple. So it's upstream. So like there's not much to talk about this, but this was more about having opportunity to talk about the concept of getting in the same boat and landing on things. So I wanted to open it up to discussion if people have questions about what this thing was and how it came
I have
to be.
questions.
Hey, surprise!
Always. So just coincidentally, I finally, hopefully, unless after this conversation, Greg is going to pull it up again, we'll have yet another driver upstream that is going to do the same thing, gets another character device that is another attestation report format in CBOR, amazingly, called NSM, the Nitro Secure module for Nitro Enclaves. And one of the things that, like, I was as part of the upstreaming process, where we were pondering about the nice user space interface to access that device, because it actually is a multi-function device that gives you an RNG, a hardware RNG, as well as random other metadata things, as well as an attestation document, right? I was pondering on how to do the attestation thing well, and I couldn't. Like, originally my reaction was, hey, sure, this could just be a sysfs file, right? Easy. Until I realized, no, you actually have a nonce that you can provide. You have a public key that gets embedded into the attestation report that you can fill in of like up to 3 kilobytes. You have another piece of random user data that can provide anything it wants in binary format that gets embedded afterwards. And so you just don't have like a simple file system like Semantic you can use for this. And then you're basically back to, oh, we should do ioctl or socket-like things, and then you're back to everything is specific anyways.
Yeah. So what I don't know is because I know there's also TPM can do attestation reports, and it has its own format.
It's much more complicated than any of the sane things.
Yeah. I mean, at least I don't know the details of your thing. This one wasn't a good fit for TPM because it's kind of like a fundamental asserting the state of the VM to start to do other things. But I saw one discussion in I think Tom Landaki and as well, we're talking about VTPM and this idea of in the attestation reports we have 64 bytes, but what the proposal was the 64 bytes you put in there is a byte that describes kind of the record, a hash of however much data you want to put in, and then like the nonce as well. And so that so with 64 bytes you can do a lot. And can we use this? I like the cleverness of just putting the hash and mixing with the nonce and get a report on that. Well, yeah. So they can use this.
Okay, maybe.
I mean, but this basically is.
Did you merge it yet? Like, is the TSM stuff?
It's merged. Yeah, I mean, but to your point about this is a multifunction device that can do other things. This is kind of also inspired by the way David Howell's the keys interface, where like you have the TPM driver. The TPM driver has its own ioctls, but it also registers a keys interface, so you can do the Linux keys can do TPM things through that ABI, but you still end up having two ABIs. But like, so this is the attestation report ABI, but like the sev guest ioctl is still there. We did intercept the Intel TDX ioctls. So there are no Intel TDX ioctls for this, but you can still have your other ioctls and have this cake as well.
Yep. Very cool.
Just getting away from the attestation stuff, I feel like with
thank you.
attestation things, it's like the tip of the iceberg. Like we're solving the stuff that doesn't actually cause the kernel that much pain when we talk about how different TDX and SMP and all the other flavors are.
Yes.
Do you see us moving the needle on the giant iceberg that's sitting below the surface?
So one of the things, so basically this is kind of like my entry into this, like if we can't simplify this, then like this is like the starter. But yeah, so then level 2 is like, I'll show a picture in the BOF about how we had a discussion with and with TDX Connect is the same, is the Intel version of AMD TIO. And I had a very productive discussion about, like, you know what, yeah, AMD drew this line in a different place. And I'm like, yes, I agree that, from my perspective, yeah, that makes it easier on the kernel. And they said, yeah, let's try to move our interface to that. So that gives me hope that we can have these discussions about, like, if not like getting people to standardize, but at least saying, like, if somebody's going off the complexity relative, we can bring them back to baseline. So we still have the mountain of complexity beneath here, but at least, like, we don't let the stray bullets fly. Oh, I thought you were trying to tackle me. Yeah, okay, good. Okay, thank you.
Right arrow, right? Right arrow? Yeah. Cool. All right, so we'll do a quick update. I think we have 10 minutes, right? Yeah. So it might be too much stuff here, but we'll just do a quick update on Cove. So Cove is the name we've been using for confidential VM extensions in RISC-V. So Atish and I will cover. We had a presentation we did last LPC where we talked about the sort of the initial foray, what the split between, where the TSM would run and what the ABI would look like. And so we wanted to just give a quick update on sort of where some of the ISA stuff is going in RISC-V more recently. So one general sort of concept we introduced in RISC-V, and this is an active TG that's working on it, so this is still under discussion in the ISA TGs, is this memory tracking table, right? So this is basically a access control architecture that allows us to sort of split the RISC-V, privilege architecture effectively vertically down the line so that you can support multiple supervisor domains. Because what we observed was whether it's like running TEs or running confidential domains, what we wanted to do was preserve the ISA so that as people are building these, TSM-like components and other things, we can institute them without, allowing them to all access the priv ISA, right? And allow some flexibility so that you don't have a particular vendor's TSM that's imposed. You can actually bring your own TSM if needed. So it gives that flexibility. So what is supervisor domains? It's basically a priv ISA extension to RISC-V that's proposed that adds this memory tracking table. And along with it, there's a couple of other sprinkling of extensions that work with the advanced interrupt architecture in RISC-V, so that once you have these separate supervisor domains, one of them could be a confidential computing domain. You can actually assign supervisor domain interrupt files to them so that you can preserve all the natural interaction with that the advanced interrupt architecture proposes, and not have to rejigger all that software that's being written for that. So just under the covers quickly, again, because of lack of time, I've put a pointer to the spec at the bottom so you can go look at the in-progress spec. The memory tracking table essentially is a very simple structure that essentially operates in conjunction with SV. SV is the paging architecture of RISC-V, which has a very similar convention of a first-level translation structure that's managed by the OS, and a second-level guest translation structure that's managed by the hypervisor extension, right? And the memory tracking structure essentially adds a physical accessor check to the PA that's coming out of the address translation, right? And it's biased more towards large pages. So you take the final PA that's coming out of the translation, you look up through the memory tracking table, and you essentially get an access or not access allowed for that supervisor domain, right? And the root for this MTT structure is hooked into the heart, which is the RISC-V convention for a hardware thread, and there's a CSR through which you program it, right? And everything is managed through, as this picture showed, through the M-mode software, right, which is the core TCB. Yeah.
Are you concerned about performance and scaling when you're checking another look-aside structure every time you want to walk a physical address?
So again, RISC-V doesn't specify implementation, but this architecture could be backed by appropriate caches. So in the worst case, you would, even after your nested walk, you would probably do one additional stuffed load if you have the right level of caching, and that should give you a reasonable performance. So at least that's based on some of the modeling that we've done. But yeah, we do expect like high performance architectures to have the right sort of caching models with the MTT structure, right? So I won't go into the bits and bytes levels of the thing. I just want to kind of point out it's biased more towards large pages because a lot of the MMU models are moving more towards large page, 2 meg, 1 gig pages. You can accommodate 4K pages as well in the architecture. And like I said, it doesn't try to
do much. It keeps things simple. It basically enforces access allowed or not allowed for the supervisor domains, right? And so we'd used this picture last time. This is sort of like a high-level bird's eye view of the Cove architecture. There's two sort of ways of thinking about it, right? On the right-hand side or on the left-hand side on that slide is the sort of the high-performance data center model of the architecture, right? Which looks very much like TDX, if folks are familiar with TDX, where you have a peer, hypervisor mode extension running as a TSM, with the M mode essentially being the core TCP that does the context switch between them. On the right-hand side, you can see a client like embedded model of this, which basically is using the second level translation structures and is running the TSM as the only root hypervisor. So in that case, you don't really need an MTT. You can just use the second level translation structures as currently defined by the H extension. The idea was to allow both these architectures and keep the ABI the same, right? So in RISC-V, you'll basically you'll see two specs, a Cove spec, which talks about the ABI, which is sort of common whether you're using a peer model TSM or a root mode hypervisor TSM. And then there is the SMMTT spec, which talks about the ISA parts, right? There's also a third spec that Samuel just started working on called the Cove IO ABI, but that essentially just extends the Cove ABI for the TEIO stuff that Samuel mentioned. Yeah.
When you talk about ABI, are you talking about guest to TSM ABI or TSM to host ABI? Or
so both. Yeah, basically the interfaces that you see here, which you could think of logically as a yeah, the interface that you see here, you could think of that as a logical interface between the host and the TSM. And then the second part is the Cove G API, which is basically the GHCX equivalent, right? Which is the guest and the TSM API. So those are both expressed in the same spec.
What's the goal of defining ABI there instead of defining at an architectural level the building blocks and letting software build things?
So yeah, so the ABI sort of reflects a lot of the RISC-V architecture specific nuances, right? That you see like in the MTT spec or the interaction with the AI spec. So it's sort of more, the analog is like, you have these verbs that the TDX module exposes, right, to the platform, right? So on the KVM side, we'll probably have common flows, like when you're donating memory or you're converting memory, things like that. But on the you can think of this ABI as sort of the lower half of that interface.
No,
Right?
I got that part. Why though? Like Intel rolled their own and wrote it all, and it's basically firmware, and they're managing it like hardware. Why are you reinventing that for RISC-V, which is much more open, and like that's the whole point of it? Like why are you defining ABI as part of the architecture that could be software, if I understand correctly?
So the ABI is software, right? I mean, all of these interfaces that you see actually, and I don't have a better picture here, but yeah, the interfaces that you see as part of the Cove H ABI or the Cove G ABI, they're all implemented as software interfaces into the reference implementations, right? So we have like a TSM implementation, right, that implements that ABI, and then we have like KVM patches that show how you invoke that ABI, right? So you need an interface into a TSM that understands on the lower half the RISC-V specific architecture.
At the same, so when you say at the lower half understands the RISC-V architecture, is the purpose of the ABI just to define things that there's only one sane way to do this for RISC-V?
No, yeah. So that's a fair point. That if somebody wants to roll a different ABI, they definitely can. That's why RISC-V calls it non-ISA. These ABI specs are all called non-ISA because they have nothing to do with the ISA for RISC-V. Right? They're tracked. If you go to the RISC-V GitHub, you'll see them under the non-ISA tree of RISC-V. Right? And the SMMTT is in the ISA tree of RISC-V GitHub because that is part of the core ISA. So Cove ABI is just one ABI. Somebody could bring like a global platform ABI and apply it with the RISC-V ISA and roll that as well.
So summarizing, this is all software that you're building on top of RISC-V hardware.
ISA, that's right.
Okay.
So we have like
okay, so the memory tracking table, to repeat, is ISA. Yes. Everything else is software defined, and okay.
Yep. So the entire right-hand model is basically completely software ABI, completely done with KVM and all the open source software. There's no hardware involved. Everything is the GCS basically. So that's the POC we did, like first, whatever very, very early code first policy we are doing and trying to adopt that.
But
And
no,
when
but remember that even in that implementation, the TSM that's shown here is specific to RISC-V ISA in the sense that it's written to the H extension as defined in RISC-V, right? The SMMTT ISA is extending that ISA and adding whatever additional things are needed for supervisor domains, but we still leverage the H extension and the existing priv ISA in
Yeah.
RISC-V.
So, like the KVM hat on from an upstream perspective, why go this route instead of like trying to extend PKVM that ARM has done?
So that I had a couple of slides after that to how do I unify ABI, and we can discuss later. So eventual goal is to use this interface to do some kind of PKVM like things, but we can discuss.
The goal here is to get a discussion going,
Yeah.
not finish the discussion.
That's.
Do
you want to talk to this?
No, we have time out. Maybe we could have given 20 minutes instead of 10. So.
Yeah, we have some starter files here for discussion. People can look at it. We'll appreciate the follow-up.
But moving on, Nikunj, thank you very much, Atish and Ravi. Suggestions the way they come.
Okay. Hello, everyone.
I'm gonna let that one go.
Okay. Yeah, my name is Nikunj Dadania. Today I'm talking about secure TSC on AMD SCV SNP guests. This is right. Okay. Yeah. So basic things, starting with what is a TSC. So x86 or any architecture uses has a counter that counts the number of processor cycles. It can be accessed on x86 by two methods. One is the legacy method of reading the TSC MSR or using the RDTSC interface. So this is pretty simple, but when you get into the guest, there are various different values that come into picture. So I'm just listing down a few of them, which is like one is the TSC raw, the TSC ratio MSR, and the TSC offset, which is part of the VMCV. The TSC ratio and the TSC offset are hypervisor controlled. So these two values, if a malicious hypervisor tries to change, it can change the view of the guest's TSC. So this basically is a security concern that the TSC value can be the guest can see a value which is does not move, or it moves at a very faster rate, right? For SCV and SCVES guest both, we have this where the guest legacy will always have it, but SCV and SCV guest also has the same issue. So the SCV SNP guests introduces a feature called secure TSC, where the values that are used to calculate the TSC in the guest is not dependent on the hypervisor controlled parameters. So when you look at the guest TSC scale and the guest TSC offset, both of them are part of the VM secure area, which is an encrypted page. So both these values are used to compute the TSC in the guest, and that basically makes sure that the hypervisor cannot change any the TSC. There is also a new MSR that has been introduced as part of the guest can read what is the frequency that the TSC is running at. The read TSC and the read TSCP instructions basically the guest side can prevent those things from getting into the host. If the host hypervisor tries to intercept those things, the VC handler intercepts that and does not allow it to go to the host. With secure TSC enabled, we could basically use it as a clock source instead of currently KVM clock is being used as a clock source, which is a parabolic clock. But when secure TSC is available, we can use that as a clock source. So going on to the next slide. Yes.
How do you envision this working with live migration, where you migrate to a VM that's running at a different core clock, and then you've got to teach something inside the guest, inside the TCB, to deal with scaling, with changing the scale if you're not letting the untrusted host push that?
Yeah.
Yeah, so the scale and the offset are part of the VMSA, right?
Yes.
And in the migration architecture that Tom talked about earlier, there is basically a portion of the SVSM that runs on both the source and destination, right? So the one on the destination, it can get information about what the physical TSC runs at on that box. And when it gets the incoming VMSA, it can calculate what the new ratio needs to be in order to keep a consistent view. And then also, of course, you need time to move forward, so it calculates an offset, similar to how it's used today, to start the TSC from that point. So it can be done in theory. It's not built yet.
Suggest go read the 5 threads that we have on dealing with TSC migration and KVM and just how many times we've got it wrong. I think we have like 5 ABIs and they all suck. So
okay,
don't write a 6th one, just reinvent one of the 5th.
This page basically talks about the flow, how the VM boots with the secure TSC. The VMM can basically configure the desired TSC frequency that it wants the VM to run at. And while updating the VMSA page, we basically we enable the secure TSC. And once the VM run happens, the secure for the boot CPUs, the guest TSC scale and the offset is programmed by the AMD security processor. But for the secondary CPUs, the values need to be queried from the AMD security processor. So the boot CPU basically needs to talk to the AMD security processor, and there is a communication channel that is encrypted using the SNP guest messages. So the message basically goes from the guest via the hypervisor, and the hypervisor relays that to the AMD security processor. That is the TSC info request message. So once that reaches the AMD security processor, it fills in the TSC offset and the TSC scale, which again comes back, and the guest decrypts that, and that is basically programmed into the secondary CPU's VMSA, and that's how it starts the auxiliary processor with the offset values and the scaling value. Yeah. So I think that's about it. And I have the patches, which is like V5 version right now, and there was a few comments related to KVM clock, where the KVM clock is selected as a clock source before secure TSC. So one of the ideas were to reduce the rating of the KVM clock to get secure TSC before that, actually. So that I did try that. It does work, but I'm not sure whether we can reduce that to, it was 299 and we can do it to 298 or something like that. And there was something that Dave Hansen pointed about using the TSC reliable that seems to be working actually. Yeah, that's about it. Yeah.
This probably seems like a silly question, but with these SCV optional features, how would the VMM know whether the guest supports these and if we can enable it at launch time or not? Like, is there any, are we too late? Could we go to the guest is running and then it says, oh, I actually want secure TSC, and we enable it?
So this is a secure SCV SNP feature. So we could enable it for any SCV SNP.
But the guest needs to have the patches, right? To do this dance.
That's
So
right. Yeah,
how
these are the guest patches. Yeah.
How do I, as the hypervisor, know if I should turn this on or not?
Okay. So if the guest does not support the patch, so
Exactly.
yeah, if the guest
doesn't
doesn't support the patch, you would fail pretty early in the guest boot, saying that this feature bit which you had enabled is not supported by the following guest.
So as someone who answers customer tickets, is there any way that we could do that better? Like before we launch the guest, can I yeah.
I was kind of hoping to catch it. So the SVSM, one of the
first things it can do is check the SCV features boot to check that they match the expected one. So that will be a way to prevent that it happens at runtime.
I think what Peter's asking is there any way we can tell if the kernel
Before.
supports it before we
Before,
launch it?
yeah.
So that you don't run into a situation where it crashes. And that's something we can probably look into
Yeah.
of seeing if there's any way to expose the supported features of a guest in some way so that you can examine it somehow. I'm not sure what we'd be able to do, but.
Yeah, thank you.
A suggestion for this and lots of other things with SVM related stuff, we might want to make a list of all the things that are requiring enlightenment in the guest to some extent and see if that pushes over the boundary of creating a paravisor. As much as I hate the idea, like there's a growing list of things that are going to be really hard to solve if we don't have host provided trusted code running in a VMPL.
So the specific problem with the paravisor, if you're thinking about the SVSM one, is every call to it is a VM exit. You slow us down enormously if we don't do guest enlightenment. I mean, we can for sort of legacy guests or things that have weird and wonderful ABIs, but if we do it for the main line, confidential computing will be so slow as to be unusable. Well, we know what it looks like for the SVSM ETPM, but it doesn't.
Yeah, that's like for this, do you have to, I'm just wondering, spitballing real quick, do you have to actually transition into VMPL 0 all that much, or can you just have it do the setup and then pass off? So you get the secure TSC stuff set up in VMPL 0 and you're happening to run at VMPL whatever. And if VMPL whatever doesn't know secure TSC, it's fine. It just doesn't crash. It just doesn't use the secure TSC, something like that.
Thank you very much for the discussion. Thank you, Nikunj. Get survey going.
Hi, my name is Saravi, and I know I'm standing between you and the beer, so I'm going to try to finish this as soon as I can. I promise. So I'm here to introduce a new security feature for an AMD processor. And the work is being done with Kishan, who's online right now, co-presenting as well. So let's get started. I'm going to skip agenda. We're going to talk about all the stuff. So AVIC. AVIC is pretty much APIC virtualization, being called AVIC, APIC V in different vendors. But ultimately, AVIC is a performance feature for virtualizing APIC, which is the interrupt controller for x86, right? With the secure AVIC, we actually redesigned the feature to add the security aspect of the virtualization here. And the three main focus is basically provide the acceleration for APIC register access, provide acceleration for IPI, and provide acceleration for device interrupt injections. Those are the three key main area, right? The interrupt injection for the device, that's not going to be covered in this because AVIC has two parts, has SVM AVIC, has IOMMU AVIC. We're not going to talk about the IOMMU AVIC in this talk, right? Secure AVIC can operate in different modes, in single VMPL mode, in multiple VMPL mode. But for the work that we've done currently, we're focusing on the single VMPL mode, which will require the enlightened guest, right? And in the VC handler is now going to be responsible for emulating other additional functionalities that not visualizing by the hardware currently. And it's only support in X2 APIC mode for the guest. So from the here's basically the hardware architecture point of view. AVIC is operating around a data structure called APIC backing page, and this backing page is managed and owned by the hypervisor, right? So think about the secure VM. The page gonna have to become part of the guest private memory. So this is one of the main difference between AVIC and secure AVIC. And along with this AVIC backing page in the guest, we also introduced another set of register called allow IRRs, which mimics what the normal IRR would be in the AVIC, which is interrupt request registers. Each bit within this register represent the vector that we want to inject interrupt normally, right? So the guest setting all this up through the guest MSR registers when it's booting. Now switch over to the host side. The change that's happening is we're getting rid of the host side APIC backing page. We introduced another set of register called requested IRR. So this is the mechanism that the hypervisor used for injecting interrupt into the guest, where it say that I want to inject this interrupt vector, and it has to match whatever the guest allow in the allow IRR before the hardware takes effect and inject interrupt into the guest, right? So from the software architecture point of view, as I mentioned earlier, there are three main focus, three main aspects of AVIC. One is, it's a little small. One is the sending API. So with AVIC, we can support different kind of API as relation. For secure AVIC, currently we only support self API. So if there's an API that's not non-self API, it's going to have to be VMXed and emulated in the VC handler by go and set the IR bit for a different VCP, the target VCPUs, right? Then it needs to VMX it out into the hypervisor so that it can go and wake up the target VCPU if it's not running. Or if that VCPU is running, it sends the doorbell to tell the running VCPU that, hey, go handle this interrupt, right? Which is kind of similar to what AVIC is normally today. Another aspect is AVIC register access relations, right? For some of the register that can be accelerated, typically it will get VMXed out. In this case, it will get VMXed out and emulated in the VC handler as well, right? And it might also VMX it out into the host to populate this yellow table, yellow box there, which is representing the shadow APIC backing page. We can talk about it, why we need to have this shadow APIC backing page in the host later, but just want to point out that it's there. The last aspect is basically the when the guest tried to when the hypervisor tried to inject emulated device interrupt, right? As I talked before, the guest needs to be modified so that it goes and set up this allow IRR bit within the guest APIC backing page, right? And then the host has to, at this point, get the guest to VMX it out and then go set up the requested IRR bit in the VMCB before VM run it back, and then the guest now can handle the injected interrupt. So this just kind of like give you the overview of where all the data structures are related to the different scenario and different level of VM exit that needs to happen.
Question on the requested IRR. Does Ucode clear the bit in requested IRR when it moves it to the guest APIC backing page?
It handles that. I'll talk it in a. I have a flow afterward too. Oh.
So the requested IRR is not really cleared by the hardware. Actually, when we do a VM exit, the software takes the responsibility for clearing the requested IRR and the update IRR bits.
Okay.
How is software supposed to know that the IRR actually got delivered to the guest?
So when we do a VM run,
the hardware actually updates the IRR bits of the backing page based on the requested IRR and allowed IRR bits. So there is like no real, real status of whether the hardware has actually delivered. But at this point, there is no feedback from the hardware, like if it has really delivered to the host, to the guest or not. So all we know is, okay, before doing a VM run, we set certain bits in the requested IRR, and then when we do a VM exit, it's kind of like assumed the hardware has already accepted the IRR, which means at least it has updated the IRR bits in the backing page. And then as part of the VM exit flow, we just clear it. And then again, during the next VM run cycle, we just again set the requested IRR bits and the flow goes, something like that.
Okay, all right. I can skip this table, which kind of show the different comparison on the different mode of AVIC. Note that AVIC and secure AVIC will be mutually exclusive. It can be enabled at the same time. And I'm going to skip this part, which is kind of like go over how the host initialize, detect and initialize the feature, which normally just look at CPU ID bit and set up the MSR. From the guest side, when it initializes a guest, it will basically set up the guest backing page and set the MSR to enable the secure AVIC feature inside the guest. The guest knows that it's running in a VM that has, on the hypervisor that has the secure AVIC features enabled because there's an MSR that when it that being exposed to the guest, so the guest can detect that as well. The part that we kind of want to point out, since we're running out of time, is basically the part where the guest needs to currently be modified to set up the allow IRR bit every time it try to update the AVIC vectors. And this is being done inside the arc-86 kernel AVIC vector.c, which maybe we would like to find a better ways to allow to set up this allow IRR bit. We look into introducing a new IRQ domain specifically for this purpose, but that's still work in progress, and we'd like to see if the community have other suggestions on.
Why do we need hardware support for this? Because if your goal is just to block IRQs, and DOS is out of scope for SMP, why can't the guest just eat the interrupts it doesn't want?
Can what, sir?
Why can't the guest just do nothing for the interrupts it doesn't want? Because I don't see how you can possibly do this race free.
Okay.
Like, what's the value add from a security perspective for letting the guest have an allowed IRR instead of just telling the guest, hey, if you don't want to die on this interrupt, just have a no-op handler, because you can't block interrupts entirely.
Let's talk offline. Not all interrupts are interrupts. Not all interrupt vectors represent devices, right? Like it.
We'll talk afterwards then.
On your slide, you skip through, you talk about the VC handler. Couldn't you have a custom APIC model that does not go through the VC handler? And wouldn't that be faster?
That could potentially, yeah. Because right now, yes, I think that could be an option.
I think we should do that.
Yeah, okay. All right. So for the current status, we are actually working on a prototype that implements what we have discussed so far, and currently we got the IPI part, the IPI injection support done, and we got the emulate device trap injection support done as well, and most of the work is being done by Kishan here. And we will successfully boot up to 128 vCPUs as a test at this point. And in the next phase, we'll work on NMI emulations support and then LPC timer emulation support.
Emulation, like we have emulation. When it's specifically for the LPC timer and the VMX, not the VMX, the TSC deadline timer, is that ever going to be fully virtualized anytime in the near future?
I don't know if I can answer that.
No.
No. Okay, get going. All right, beer is coming. So one of the issues that we are trying to resolve currently is that there's a requirement for the guest epic backing page to always be present in the nested page table. And right now we kind of run into issue with the KVM MMU ZAP PTE because it just take that away. So the workaround right now is we just invoking the KVM TDP MMU map before we do the VM run, but that does not always work. So we'll probably need to figure out a better way to do that offline. All right. Thank you.
Thank you, Suravi. Before getting you to the beer, I want to just take a moment to thank all the folks involved here. I want to thank our sponsors. I want to thank James and the rest of the LPC organizers. I want to thank Jörg, who's helped a lot in organizing this. Well, he did most of the work. Thank you to all our speakers. And most importantly, thank you to all of you for making this a great discussion. And we need to continue these discussions over beer. Bye.
But it's fairly easy.